Hello, and welcome to Sleep Gravity. In a quiet room, temperature rarely changes in a way we can notice immediately. When a heater is first turned on, the air does not suddenly become warm all at once. Heat appears first around the source, then slowly spreads across the floor, along the walls, and into the blankets and furniture. The body may not notice these subtle changes until, at some point, we realize that the room has quietly become more comfortable. When the heat is turned off, the reverse process unfolds just as gradually. The warmth does not disappear at once, because the room still holds traces of the energy it has absorbed. Hundreds of light years away, there is a planet that preserves a memory of heat in much the same way. It is a giant world wrapped in layers of gas so deep that the idea of a clearly defined surface nearly loses all meaning. There are no oceans beneath the sunlight, no continents for day and night to pass across, and no level ground where an observer could stand. There is only atmosphere, currents of gas in constant motion, and the immense weight of layer upon layer of matter, pressing downward as the depth increases. At this moment, the planet is in the most distant part of its journey around its star. Light still reaches it, but the star appears smaller and gentler than it will later become. Less energy falls into the atmosphere, and so the world is passing through a relatively quiet period. The upper layers of gas are slowly releasing the heat left behind from the previous close approach, while currents far below continue to carry energy silently from one region to another. Quiet here does not mean complete stillness. On a giant gaseous planet, the atmosphere can flow in broad bands that circle the entire world. Warmer regions rise, cooler layers sink, and unfamiliar clouds may form and dissolve in the darkness. But for now, everything unfolds slowly enough for the atmosphere to adjust. The energy arriving from the star does not change too quickly. Heat has time to spread, winds have time to redistribute it. The planet seems to be holding on to a delicate state of balance. If we could hover above those cloud layers and look toward the star, we might sense nothing unusual approaching. The star would still appear as a distant disk of light. Its brightness would change too little from one day to the next to offer any clear warning. The atmosphere would continue moving to its own rhythm, like a room gradually cooling after the heater has been turned off. Everything might seem capable of continuing this way for a very long time. But this planet follows an orbit unlike those of most worlds familiar to us. It does not travel around its star in a nearly circular path, where the distance changes only slightly over the course of a year. Its route is stretched into a long, narrow arc, carrying the planet far from the star for most of its journey before suddenly bringing it back toward a region of far more intense light. Here, at its greatest distance, the planet moves relatively slowly. Yet the star's gravity is always acting upon it, gradually drawing its path inward. The distance begins to shrink, at first so slowly that the change is almost impossible to detect. Then, with each passing day, the planet falls deeper into the star's gravitational field. It accelerates, the star grows larger in the sky, and the amount of light pouring into the atmosphere begins to rise. No cloud on the planet knows this. No wind can count the days that remain. The world simply continues along the path it has followed again and again for an immense span of time. But measured by a human clock, only a few dozen days remain before the present calm is broken. During that interval, the earliest changes may still be very subtle. The light grows slightly stronger. The upper layers of the atmosphere absorb more energy. Some clouds may begin to thin, while once stable winds gradually respond to new temperature differences taking shape. No sudden shock has arrived yet, but the atmosphere has already entered a transition it cannot stop. What makes this planet remarkable is not simply that it is approaching its star. Many other worlds exist very close to their stars and endure intense heat throughout their lives. But this planet is given a long period of rest. It has time to move away from the source of heat, time to cool, and time for its atmosphere to return to something close to a stable state. Then its own orbit drives the entire world back into a completely different environment. When that moment arrives, the star will not merely become a little brighter. the energy falling onto the planet will increase so rapidly that the atmosphere will no longer have enough time to adjust as gradually as before. One side of the world will be heated first, while other regions still retain the temperatures of the previous state. Winds will have to carry enormous amounts of energy between areas that are becoming increasingly different. Molecules that remain stable in cooler air may enter new reactions, while clouds that endured through the quiet period may change as the heat reaches them. In only a few hours, the temperature in part of the atmosphere may rise by hundreds of degrees. And that is what makes this world so extraordinary. A planet far larger than Earth, carrying an immense atmosphere, can be pushed from a relatively calm state into a violent surge of heating in no more time than a single human afternoon. How can an entire world change so quickly? How can it repeatedly enter a region of extreme heat, endure that sudden warming, then move away and begin cooling again before the entire cycle starts over? The answer does not begin with the clouds or the winds, but with the unusual shape of the path the planet follows. For now, it is still far away. The star remains small in the sky, the atmosphere continues in its slow rhythm, and calm still surrounds this enormous world. But ahead, the orbit is gradually curving inward. The light will grow stronger, the planet will move faster, and this long interval of quiet is slowly, silently coming to an end. The path now quietly curving inward belongs to a world whose name suggests no color, sound, or emotion. HD 80606b. It sounds more like a line of code taken from a data table than the name of a planet moving among the stars. Yet behind those cold letters and numbers lies one of the most unusual worlds humanity has ever discovered beyond the solar system. HD 80606b is located more than 200 light-years from Earth. This means that the light now carrying information about it to us left that star system more than 2 centuries ago, at a time when many modern cities still had no electricity and the possibility of confirming the existence of planets beyond the solar system remained outside the reach of human observation. When telescopes collect light from this star, we are not seeing it as it is now. We are receiving a very old image, sent across a distance so vast that even light requires several human generations to complete the journey. The star this planet orbits is called HD 80606. It belongs to the same general class of stars as the Sun, so from a distance, the system might seem somewhat familiar. A pale yellow star, stable through most of its lifetime, shining into the space around it. But the world moving beside it is nothing like Earth, nor is it anything like a rocky planet that might carry oceans or a solid surface. HD 80606b is a gas giant. The closest way to picture it is to begin with Jupiter, the largest planet in our solar system. Both worlds are wrapped in thick layers of gas, possess powerful gravity, and have no clearly defined ground where a human being could stand. But HD 80606b is more than 4 times as massive as Jupiter, while its size is only roughly comparable to that familiar giant planet. At first, this may sound strange. If a planet contains far more material, we might expect it to expand by a similar amount. But matter inside a gas giant does not behave like a balloon being filled with more air. As mass increases, gravity also becomes stronger, compressing the layers of gas more tightly together. The added material does not simply make the planet larger. It also places the interior under greater compression. As a result, HD 80606b contains the mass of several Jupiters without becoming a sphere 4 times as wide. If we could begin a journey downward from the upper atmosphere, we would find no clear boundary marking where the sky ends and the ground begins. At first, the gas might be extremely thin, but the deeper we traveled, the greater the pressure would become, and the denser the surrounding layers of matter would grow. Light from the star would gradually fade and eventually disappear altogether. Temperature and pressure would continue rising until the gas no longer resembled the light, gentle air around us. At great depths, matter may be compressed into states that human beings almost never encounter in everyday life. For that reason, calling HD 80606b a sphere of gas can sometimes make it sound more fragile than it truly is. This is not an enormous cloud that could simply be blown apart. It is a massive world, held tightly together by its own gravity, with one atmospheric layer continuing into another across an immense depth. What telescopes can observe comes mainly from the very thin outer region, where starlight is absorbed, reflected, or radiated back into space. Beneath that visible layer lies most of the planet, submerged in pressure and darkness. Its great mass also helps explain how HD 80606b can continue to survive after countless passages through the region of extreme heat near its star. During each close approach, the upper atmosphere is heated intensely, but the entire planet cannot warm all at once. The deep interior contains too much material and has too much thermal inertia to respond as quickly as the outer atmosphere. Much like a deep lake that warms mainly at the surface during a sunny day, this world can experience a powerful temperature surge above, while most of its interior changes far more slowly. This does not mean the outer atmosphere is protected from upheaval. On the contrary, the contrast between an outer layer that reacts quickly and deeper regions that respond slowly is part of what makes the planet's weather so unusual. Energy from the star is first captured in the layers that light can reach. Heat builds there, causing the gas to expand, changing the pressure, and beginning to drive vast currents through the atmosphere. While the upper layers struggle to adjust to a new environment, the regions below still carry the thermal state of the quieter period that came before. Because we cannot see HD 80606b as a sharply resolved globe, much of our image of it must be reconstructed from light and physical models. There is no photograph showing the true colors of its cloud bands, the shapes of its swirling winds, or the appearance of the deeper atmosphere below. The images commonly used to portray the planet are interpretations created by artists and scientists, translating data into scenes the human eye can understand. That does not make this world any less real. Instead, it reveals how much humanity can learn from an extraordinarily small amount of light. We can estimate the mass of a planet without ever seeing it clearly separated from its star. We can infer its size as it passes in front of the starlight, then follow changes in temperature as it approaches the source of heat. Each measurement offers only a small fragment, but when those fragments are placed together, an entire world begins to emerge. The name HD 80606b also comes from the way science assembles information piece by piece. The first part is the name of the star in an astronomical catalog. The lowercase b indicates that this was the first planet discovered orbiting that star. It is not a name drawn from mythology, nor does it carry any meaning connected to fire or storms. It simply identifies the planet within the growing system of human knowledge among the thousands of other distant worlds that have now been found. And yet, sometimes the contrast between a name and the nature of the world behind it makes a planet even more memorable. HD 80606b sounds like a silent entry in a database, but in reality, it is an enormous sphere being drawn between two nearly opposite states during every orbit. In the distant part of its journey, the atmosphere has time to release heat and slowly settle. When the planet returns close to its star, that same atmosphere must absorb a stream of energy, increasing at an almost unimaginable rate. And here an important detail begins to emerge. This world is not unusual simply because it is large, massive, or hot. The galaxy contains gas giants that are even heavier, as well as planets that remain close to their stars and maintain even higher temperatures. What sets HD 80606b apart is the change itself. It does not live forever inside the furnace. It repeatedly enters that furnace and then leaves it behind. To understand how such a massive planet can pass through two very different environments within a single short year, we must look beyond the clouds and follow the path of the entire world. More than any other feature, it is the orbit that has transformed HD 80606b from an ordinary gas giant into a natural laboratory that astronomers can observe from an extraordinary distance. Its name may sound cold, but the path it follows is anything but. Not just a little. The energy falling onto the planet will increase so rapidly that the atmosphere will no longer have enough time to adjust as gradually as it once did. One side of the world will be heated first, while other regions still retain the temperatures of the previous state. Winds will have to carry enormous amounts of energy between areas that are becoming increasingly different. Molecules that remain stable in cooler air may enter new reactions, while clouds that endured through the quiet period may change as the heat reaches them. In only a few hours, the temperature in part of the atmosphere may rise by hundreds of degrees, and that is what makes this world so extraordinary. A planet far larger than Earth, carrying an immense atmosphere, can be pushed from a relatively calm state into a violent surge of heating in no more time than a single human afternoon. How can an entire world change so quickly? How can it repeatedly enter a region of extreme heat, endure that sudden warming, then move away and begin cooling again before the entire cycle starts over? The answer does not begin with the clouds or the winds, but with the unusual shape of the path the planet follows. For now, it is still far away. The star remains small in the sky, the atmosphere continues in its slow rhythm, and calm still surrounds this enormous world. But ahead, the orbit is gradually curving inward. The light will grow stronger, the planet will move faster, and this long interval of quiet is slowly, silently coming to an end. The name HD 80606b may sound cold, but the path it follows is anything but. On a small diagram, its orbit might look like a simple closed loop around its star. Yet when placed beside Earth's orbit, the difference becomes immediately clear. Earth travels around the Sun along a slightly flattened path, but the flattening is so subtle that, to the eye, it still appears almost circular. The distance between Earth and the Sun changes over the course of a year, but not enough to turn our planet into two entirely different worlds at opposite ends of its orbit. HD 80606b is different. Its path is stretched so dramatically that it resembles the orbit of a comet more than that of a giant gas planet. For most of each revolution, it remains relatively far from its star. Then the curve suddenly carries the planet into a much narrower region, where the distance shrinks rapidly, its speed increases, and every condition around it begins to change. A year on this world is not a sequence of days passing beneath a relatively steady source of light. It is more like a long journey through a quiet realm, ending in a brief but violent close approach. In astronomy, this kind of path is called an ellipse. We can picture an ellipse as a circle stretched outward in two directions, but that image describes only its outer shape. What matters more is the position of the star. In an ideal circular orbit, the star would sit at the exact center of the path. In an ellipse, however, the star is displaced from the geometric center and lies at a point called a focus. That offset creates two very different regions, one where the planet is farthest from the star and another where it comes closest. The difference between those two distances for HD 80606b is almost difficult to believe if we are familiar only with the solar system. At the distant end of its orbit, the planet lies at roughly the same distance from its star as Earth does from the Sunday. But at the opposite end, it moves about 30 times closer. This entire change occurs within an orbit lasting around 111 days. In other words, a year on HD 80606b is shorter than 4 months on Earth. Yet within that brief year, the planet experiences a far greater change in distance than our world ever does. Astronomers use a quantity called eccentricity to describe how elongated an orbit is. A perfect circle has an eccentricity of 0. The closer the number moves toward 1, the more stretched the orbit becomes. HD 80606b has an eccentricity of about 0.93. placing it among the planets with the most extreme orbits ever discovered. Yet that number becomes meaningful only when we imagine its consequences. It does not simply tell us that the path is slightly distorted. It tells us that the planet's distance from its star changes so greatly that both the rhythm of its motion and its thermal environment are transformed during every revolution. A gentle way to picture this is to imagine a very long-running track stretched into a narrow oval. At the outer end, the runner follows a broad curve where everything seems extended and slow. But as the runner enters the opposite end, the track tightens around a bright point, and that nearby section is crossed much more quickly. This does not happen because the planet chooses to change its pace, but because its motion is always bound to the gravitational field of the star. Centuries ago, Johannes Kepler recognized that planets do not move at the same speed at every point in their orbits, but when they are farther from their stars, they travel more slowly. When they move closer, they speed up. This law applies to Earth, Mars, and the other planets of the solar system. But on HD 80606b, the effect becomes far more pronounced because the orbit is so elongated. Most of the 111 days are spent in the broad, distant region. The close encounter with the star occupies only a short portion of the journey. Yet that brief interval defines much of what makes this planet so remarkable. If a year on Earth is felt through gradual changes in light, temperature, and season, then a year on HD 80606b follows an entirely different rhythm. It does not have seasons in the familiar sense, because its greatest changes do not come from the tilt of its axis, but mainly from its changing distance from the star. At the far end, the light is weaker and the atmosphere has more time to release heat. As the planet moves inward, the amount of energy it receives begins to rise. Near the closest point, the change no longer unfolds slowly like a season shifting. Instead, it gathers into a rapid episode of heating on a global scale. It is important to understand that an elliptical orbit does not mean the planet is losing control or gradually falling into the star. This path remains a repeating orbit. Each time HD 80606b plunges inward, it does not continue descending forever. Its sideways velocity allows it to sweep past the closest point, curve around the star, and travel outward again. Gravity pulls it inward, but its existing motion prevents it from falling straight down. Together, these two effects create a closed loop in which the close approach repeats every 111 days. The process can be imagined as an object sliding through the bottom of a deep valley. As it descends, it accelerates. After passing the lowest point, its momentum carries it upward along the other side. Without enough motion, the object would stop at the bottom. But HD 80606b always carries tremendous speed, enough to pass through the region nearest the star and begin moving away once more. So the phrase "falling into fire" does not describe a plunge that ends in collision. It describes a deep passage into a region of intense radiation before the orbit carries the planet back out again. This unusual shape turns HD 80606b into a rare natural laboratory. Many hot gas giants remain close to their parent stars at all times, so their atmospheres exist in a continuously heated environment. Scientists can observe that state, but it is difficult to isolate the process by which an atmosphere responds when the source of heat changes. With HD 80606b, nature has created a repeating experiment. The planet begins far away, moves inward, heats rapidly, then retreats and slowly cools. Each orbit is like placing the same atmosphere into a series of profoundly different conditions. Because of this, astronomers can ask more than simply how hot the planet becomes. They can investigate how quickly it warms, which atmospheric layers respond first, how heat is transported, and how long the atmosphere takes to return to a quieter state. All of those questions begin with an ellipse that might otherwise look like nothing more than a simple shape drawn on paper. At its farthest point, the planet is still traveling through the broad portion of its orbit. The star does not yet occupy much of the sky, and the greatest changes still lie ahead. But the curve cannot continue in that direction forever. With each passing day, HD 80606b moves away from the most distant region and begins its return. The distance narrows slowly at first, then more quickly as the planet falls deeper into the star's gravitational field. Its 111-day year has begun to close toward the narrowest end of the ellipse. The quiet will not disappear all at once, but the rhythm of motion has already changed. The planet is leaving the distant region where it once had time to cool and is moving toward the section of its orbit where light, temperature, and speed will rise step by step. To understand what is about to happen, we must remain a little longer at that farthest point where this world still carries the calmest appearance it will have during its entire short year. At the far end of its orbit, HD 80606b seems to have temporarily escaped the most violent part of its year. The star is still there, still shining upon the upper layers of the atmosphere, but from this distance, the heat is no longer arriving with the same intensity it will bring during the planet's close approach. If we could observe from a safe place among the clouds, we would see the star appearing smaller in the sky, its light gentler, while the entire world seemed to drift through a long interval of rest between two periods of upheaval. The distance between the planet and its star is now roughly comparable to the distance between Earth and the Sunday. But that does not mean the environment here resembles Earth. HD 80606b has no blue oceans, no thin atmosphere, and no solid surface to regulate heat in familiar ways. It is a gas giant, filled with deep layers of matter, immense pressures, and internal heat that continues to escape over time. For that reason, describing this place as cold would create the wrong impression. Even at the most distant point in its orbit, the upper atmosphere may remain far hotter than anything humans would find comfortable. This is not a frozen world drifting quietly through darkness. It is simply in a region where the heating is less intense, where less energy arrives from the star and the atmosphere has more time to adjust. That distinction is important. On Earth, when clouds weaken the afternoon sunlight, temperatures near the ground can fall relatively quickly. But on a gas giant, the entire system does not respond all at once. Its atmosphere contains an enormous mass of material, and that material can retain energy for a very long time. We might picture a large pot of water that has just been removed from the stove. The flame is gone, but the water does not immediately become cold. The water near the sides of the pot begins losing heat first, while the deeper regions continue to hold their energy. Convection currents slowly carry warmer water upward and cooler water downward. For a long while, the entire pot remains warm even though the external heat source has disappeared. The atmosphere of HD 80606b carries a similar kind of thermal memory. As the planet moves away from the region near its star, the upper layers of gas begin radiating energy into space. Yet the deeper interior still holds heat from the previous close approach. That energy does not remain fixed in one place. It continues to move through atmospheric currents, convective regions, and large-scale motions within the planet. The ability to retain heat and respond slowly to changes in incoming energy is known as thermal inertia. An object or environment with high thermal inertia does not heat up immediately when exposed to light, nor does it cool the instant that light grows weaker. It needs time to absorb, distribute, and eventually release that energy. A room in the evening can offer a familiar sense of this process. After the heater has been turned off, the air does not immediately become cold. The floor, the walls, the blankets, and the furniture still hold warmth, slowly releasing it into the surrounding space. For a while, the room continues to carry the comfort of a heat source that is no longer active. Only after enough time has passed does that warmth gradually fade. On HD 80606b, this process unfolds on the scale of an entire world. There are no walls to hold in the heat, but the planet's immense mass of gas serves a similar role. The deeper layers contain more energy, while the upper regions exposed directly to space can cool more quickly. As a result, the atmosphere does not return to a perfectly uniform state. Some regions still carry traces of the previous heating event, while others have already begun settling beneath the weaker light. Here, at the distant end of the orbit, the planet's motion is also slower. Far from the star, it no longer races forward as it does during the closest part of its journey. The distance changes more gradually, so the amount of light received from one day to the next does not vary as sharply. This is the longest part of its 111-day year, where the planet spends more time crossing the broad outer region of its orbit. That slower pace gives the atmosphere something rare: time. Winds can continue carrying heat from one region to another without facing a sudden surge of incoming energy. The upper layers can gradually release some of their warmth. Chemical reactions have a chance to move closer to equilibrium, while clouds, if they exist, may form under conditions that change less dramatically. Yet even during this period of rest, HD 80606b is not completely still. Beneath its somewhat calmer appearance, heat from deep within the planet continues to rise. Warmer regions of gas may drift upward, while cooler layers sink, forming vast cycles of convection. The winds do not necessarily stop. They simply move within an environment that is under less pressure from the star's radiation. Seen from a great distance, the planet would reveal very little. It is only a tiny dark point beside a star millions of times brighter. There is no way to see its cloud bands clearly or follow individual currents moving through the atmosphere. But through infrared light, scientists can detect that the world is radiating heat and that its temperature changes as it moves through its orbit. Those changes reveal that the planet is not responding only to the present, it is also carrying its past. While it remains in the distant region, the atmosphere still holds some of the energy it absorbed many days earlier. And when it begins approaching the star once again, it will not start from a state that is completely cool or perfectly balanced. It will enter the next heating event with an atmosphere that already has a history, already contains motion, and already carries a reservoir of internal warmth. This makes every close approach more complex than a simple change in temperature. The star is not heating a motionless atmosphere. It is acting upon a dynamic system where different layers respond at different speeds and where old energy has not entirely disappeared before new energy begins to arrive. At the far end of the orbit, the sense of isolation seems to widen. The star appears smaller in the sky, while the surrounding space opens into darkness and depth. The planet spends most of its short year here, moving slowly through the region of weaker heating, as though stretching out the final days of a long rest. But that rest cannot last forever. Although its motion is still slow, the orbit has already begun carrying HD 80606b inward again. At first, the star brightens only slightly, so little that the atmosphere may hardly register the difference. Then the distance will shrink more quickly, the planet's speed will rise, and the amount of energy pouring onto this world will begin changing at an entirely different pace. The distant region has given the planet time to cool, but not enough time to erase the memory of its previous heating. Now, as the star gradually grows larger ahead, this immense atmosphere carries all of its remaining warmth into a journey where the quiet will soon become impossible to maintain. The most distant region had given the planet a long interval of rest, enough for the upper layers of gas to cool somewhat, enough for the starlight to grow gentler, and enough for the entire world to seem as though it had recovered its steady rhythm. But along an orbit stretched this far, calm is never a permanent home. It is only a broad, slow section of the journey before everything begins to narrow again. At first, almost nothing remarkable seems to happen. The star remains small in the sky. Bands of gas continue drifting past one another, and the heat stored from the previous close approach keeps escaping from the atmosphere little by little. If we could stand outside the system and watch for several days, we might notice no obvious change at all. The planet would still be moving through the distant part of its orbit, so quietly that it might seem to be drifting across the darkness rather than returning towards something violent. And yet, the orbit has already begun to curve inward. There is no moment when the planet stops and turns around. It has never truly been still. Throughout its long period of rest, it has continued moving forward, while the gravity of the star has steadily bent its path. At first, the curve is so gentle that it is nearly impossible to notice. But with each passing day, the direction of motion shifts a little more, the distance decreases a little further, and the brighter region ahead slowly draws closer. What is happening can be imagined as a stone beginning to roll down into a very deep valley. Near the upper slope, the incline is still gentle, so the motion is slow and smooth. The stone seems to move only slightly under the faint pull of gravity, but the farther it descends, the steeper the slope becomes, the faster it travels, and distances that once required a long time to cross begin to pass more quickly. No hand is pushing the stone. No engine is accelerating the planet. Gravity carries out the entire process in silence. While it remains far from the star, this giant gaseous world is like an object resting high on the slope of a gravitational valley. It carries energy because of its position, even though there is no mountain or height in the familiar sense. As it falls inward, some of that energy becomes motion. The planet speeds up not because it receives more fuel, but because it is moving deeper into the gravitational field of the star. This is one of the quiet beauties of orbital mechanics. A world can accelerate across millions of kilometers without any engine at all, simply by allowing gravity to perform the work that was set in motion when the orbit first formed. The closer the planet moves to the star, the stronger the pull becomes. And as its speed increases, it crosses each section of its path in less time, making the inward plunge feel more pronounced with every passing day. Even so, it is not falling directly into the star. In everyday life, when we think of gravity, we usually picture something being pulled downward, a leaf falling from a branch, a stone released from a hand, or a drop of water descending toward the ground. But in space, gravity can create a far more subtle kind of motion. If an object is already moving sideways fast enough, it will keep falling toward the source of gravity, while also continuing to miss the place it is falling toward. The moon is always falling toward Earth, but its sideways motion carries it around our planet instead of allowing it to strike the surface. Earth is falling toward the sun in much the same way. And in this distant star system, the giant planet is also falling toward its star, though its highly elongated orbit makes that descent far more dramatic. We can return to the image of the valley. The stone rolling downward is not aimed at a wall at the bottom. It carries enough motion to pass through the lowest point, change direction, and begin climbing the opposite slope. In space, that valley does not exist as physical matter. It is only a way of picturing gravitational energy. But the rhythm of motion remains similar, speeding up on the way inward and slowing down on the way out. So this planet is not losing control, nor does each orbit carry it slightly closer to the star until it is finally consumed. Over the period humans have observed it, this is a repeating path. The world plunges inward, sweeps past the closest region, and then travels outward again. It gradually slows, passes through another long interval of rest, and eventually begins the entire journey once more. But even though the path repeats, what happens to the atmosphere during the inward plunge is deeply unusual. In the distant part of the orbit, conditions change slowly enough for the layers of gas to adjust. Heat is carried from one region to another. The upper atmosphere radiates some of its energy into space, and large-scale motions can gradually settle into a relatively stable state. As the planet returns inward, however, the external environment begins changing faster than the interior can respond. At first, the difference remains small. The starlight grows slightly stronger, but the deeper layers of gas feel very little of it. The atmosphere is like a large pot of water that has just been placed back on the stove. The flame has appeared, but the water still holds its previous temperature. The region nearest the bottom receives energy first, while the upper portion responds more slowly. Time is needed for the heat to spread, for convection currents to begin moving, and for the entire pot of water to truly change. On this planet, the process is far more complex. The thin, high layers of gas receive the additional radiation first. Farther below, denser matter still carries traces of the period spent far from the star. Part of the atmosphere has already begun entering new conditions, while another part still remains within the old state. Two different moments seem almost to overlap within the same world. This mismatch in timing creates the sense that the planet is being pulled away from equilibrium. Not because the system has stopped working, but because its different parts can no longer keep pace with one another. Orbital motion accelerates first, the light changes next. Temperature responds a little more slowly. Winds, clouds, and chemistry require still more time to react. The entire atmosphere becomes like an orchestra, struggling to maintain its rhythm while the conductor quietly increases the tempo. With each passing day, the star grows slightly larger in the sky. Its light no longer carries the distant quality it had in the outer orbit. It becomes more concentrated, more distinct, and increasingly difficult to ignore. Changes that were once almost imperceptible begin accumulating into a trend that cannot be reversed. The planet has already moved too far down the slope of the valley to return immediately to its slower pace. At the most distant point, nearly an entire day may pass with very little change in distance. But as the planet moves inward, that same amount of time carries it across a much greater span. Quiet weeks gradually give way to faster days, then to hours during which the external conditions change strongly enough that the atmosphere must respond almost continuously. There is no sound in space to announce this new phase. No visible boundary marks the place where the period of rest ends and the acceleration begins. There is only a sequence of small changes, each one following the last, until the entire world no longer resembles the one that existed only a few weeks before. HD 80606b has not yet reached the hottest part of its orbit. The star does not yet dominate the sky, and the temperature surge of hundreds of degrees still lies ahead. But the orbit has now carried the planet completely out of the quiet region. Its speed continues to rise, the distance continues to shrink, and the atmosphere is beginning to recognize that the source of light is changing faster than it can slowly adjust. The imaginary stone is still rolling down the valley, moving faster with every moment, but it will not strike the bottom. It will sweep through the deepest region and continue upward along the other side. Before it can do that, however, it must pass through the place where the star appears closest, where the light is not only brighter, but also carries enough energy to transform the entire observable atmosphere. From this point forward, the story is no longer only about motion. The shrinking distance will cause the incoming light to increase in a way far more dramatic than our ordinary experience might suggest. And as the star begins to grow larger in the sky, the planet will soon discover that its inward plunge is not merely carrying it faster, but drawing it toward a furnace opening wider before it. The inward plunge does more than make the planet move faster. With each passing day, the sky ahead quietly begins to change. The disk of light that once appeared so small in the distant region now starts to expand. At first, so slowly that the difference is difficult to notice, then more clearly as the distance continues to shrink. The light no longer carries the remote, relatively gentle quality of the earlier interval of rest. It becomes more concentrated and more intense, as though the entire star system were gradually tilting toward a source of heat that occupies more and more of the space ahead. If we could observe from above the cloud layers, we would not see the star suddenly swell overnight. The change unfolds continuously, through one small step after another. Yet along the elongated orbit of HD 80606b, those steps do not continue at the same pace. The closer the planet moves, the more rapidly the distance decreases, and the faster the bright disk grows. What was almost unnoticeable in the outer region begins to become the most prominent feature in the sky. The idea that a distant object appears larger as it approaches is deeply familiar. A light at the end of a hallway occupies only a tiny point in our field of view, but as we walk toward it, it gradually expands, its edges become clearer, and its glow grows brighter. For this planet, the change does not unfold across a few meters inside a room, but across tens of millions of kilometers. The scale is almost impossible to imagine, yet the principle remains the same. As the distance decreases, the source of light occupies a larger portion of the sky and delivers more energy to every region of the atmosphere. But light does not increase in the simple way our everyday intuition might suggest. If we stand twice as close to a light bulb, we do not receive merely twice as much light. Energy radiating from a source spreads outward in every direction, like the surface of a sphere expanding continuously through space. The farther it travels, the more widely the same amount of energy must be distributed, so each square meter receives a smaller share. As we move closer, the process reverses. The energy becomes concentrated over a smaller area, and its intensity rises much faster than the distance falls. Physicists call this the inverse square law. The name may sound dry, but the image behind it is quite simple. Imagine light from a lamp spreading across a sheet of fabric. Close to the source, the illuminated area is small and intense. Move the fabric farther away, and the bright region expands, but the total energy does not increase. It is simply spread more thinly across a larger area. Bring the fabric closer again, and the illuminated region contracts and grows stronger. On HD Doppeldalen 90 Bay, the atmosphere is that immense sheet, moving steadily closer to the source of light. What makes this journey so extreme is the enormous difference between the two ends of the orbit. At its farthest point, the planet lies at roughly the same distance from its star as Earth does from the Sunday. But near its closest approach, that distance becomes only a small fraction of what it was before. The stellar disk may therefore appear many times larger in the sky, while the amount of energy pouring into the atmosphere rises to nearly 1,000 times what the planet receives in the distant part of its journey. This does not mean the entire planet instantly becomes 1,000 times hotter. Temperature does not respond in direct proportion to the amount of incoming light, and the atmosphere does not absorb every wavelength in the same way. Some energy is reflected, some is captured at different altitudes, and some is carried away by winds or radiated back into space as infrared light. Even so, the change in incoming energy is large enough to push the atmosphere into a state entirely different from the quiet interval in the outer orbit. On Earth, the Sun appears to remain nearly the same size throughout the year. Our orbit is only slightly elliptical, so the change in distance is small. The seasons are driven mainly by the tilt of Earth's axis, which causes each hemisphere to receive sunlight at different angles. On this giant gaseous world, the story is almost reversed. Its orbit is so elongated that distance becomes the dominant factor. Its seasons do not arrive gradually through changing angles of sunlight over many months. They are governed by a rapid approach toward the star. During the early stage, the upper atmosphere receives only a moderate increase in energy. The difference may blend into the variations already present within the atmosphere. But as the bright disk continues to grow, the source of heat no longer changes slowly enough for the system to maintain balance with ease. Each hour brings a new set of conditions. Just as one layer of gas begins adjusting to the present level of radiation, the next level has already become stronger. It is like trying to keep a room at a stable temperature while someone continuously turns the heater higher. If the heat rises slightly and then stops, the room can gradually settle into a new state. The walls, floor, and furniture absorb warmth, the air circulates, and eventually, everything approaches another balance. But if the heater keeps growing stronger before that process is complete, the room is always falling behind the change. The air responds first, solid objects respond later, and nowhere has enough time to become fully stable. On a planetary scale, this delay creates atmospheric regions in very different states. The side facing the star receives direct radiation and begins heating more strongly. Areas farther from the point of most intense illumination preserve the older conditions for longer, while the deeper layers continue to carry the thermal inertia of the previous phase. The atmosphere does not warm as a single uniform body. It is stretched between several states, where temperature, pressure, and motion all begin to drift away from their familiar rhythm. The growing stellar disk also changes against the character of light across this world. In the distant region, the source may have resembled a small and solitary sun against the darkness. As the planet moves closer, the star not only becomes brighter, but expands into a much larger presence, occupying more of the sky and pouring an increasingly dense stream of energy onto the clouds. There is no solid surface where the light can cast familiar shadows, but within the atmosphere, radiation still leaves its mark through temperature, brightness, and the way molecules absorb different wavelengths. If an instrument could hover safely among the cloud layers, it would not need to look directly at the star to know that the distance was shrinking. Thermal sensors would detect the change first. Pressure and wind speed would begin to shift away from their former state. Higher layers of gas might expand as they absorbed more energy, while deeper regions responded more slowly. Each signal might be subtle at first, but together they would reveal that the entire world was entering a new phase. Here, light does more than allow us to see the planet. It is also the force shaping it. Every photon entering the atmosphere carries energy. A single photon is almost insignificant, but the immense number arriving continuously from the star can excite molecules, alter chemical reactions, and create the temperature differences that drive the winds. A world does not need to touch fire in order to be heated. It only needs to enter a region where the flow of radiation becomes powerful enough. Even so, the greatest rise in temperature has not yet arrived. The planet is moving faster, but part of the orbit still remains before it reaches its closest point. The bright disk continues to expand, and each additional decrease in distance brings a greater increase in incoming energy than the one before. This is why the final days of the approach matter more than most of the journey that preceded them. Within a brief interval, conditions can change more than they did during the long weeks spent in the distant region. At first, the rising pace resembles a piece of music played slowly, with enough space between each note for the listener to notice every change. But as the planet draws closer, the notes begin to crowd together. The light intensifies, the speed increases, and the atmosphere must respond without pause. There is no sudden outbreak of chaos, only a rhythm growing steadily faster until the earlier calm no longer has room to remain. HD 80606b is still the same world that drifted through the distant part of its orbit. Its mass has not changed, its deep atmospheric layers are still there, and the thermal memory of the previous approach has not completely faded. But the environment around it is different now. The star that once appeared so small is becoming a much larger disk of light, and the space that gave the planet so much time to cool is rapidly closing. Only the shortest and most violent part of the year now lies ahead. During the hours surrounding closest approach, the light will intensify until the observable atmosphere can no longer maintain its former state. Temperatures will climb rapidly. Winds will respond to the growing differences, and a planet that once seemed calm in the distant region will enter the most intense heating phase of its entire orbit. The star has now grown too large to be regarded as a distant point of light. It is becoming the overwhelming center of the sky, while the giant gaseous world continues rushing forward, separated from the furnace by an interval measured no longer in many weeks, but in days and then in hours. The star is no longer a small point of light suspended far away in space. In the planet's sky, it has expanded into a prominent glowing disk, growing larger with every passing hour, and pouring an increasingly powerful stream of energy into the atmosphere. The journey that has unfolded over many weeks is entering its shortest phase, where the most violent part of a 111-day year is compressed into a few days and then into only a few hours. The giant, gaseous world is approaching the closest point in its orbit around the star. Astronomers call this position periastron, but there is no invisible doorway marking the moment when the planet enters a completely different realm. The distance simply continues to shrink, its speed continues to rise, and the amount of light falling onto the atmosphere grows ever. Its speed continues to rise, and the amount of light falling onto the atmosphere grows ever greater, until the entire system is pushed far beyond its previous state of relative stability. At its closest approach, the planet is only about 0.03 times the distance between Earth and the Sun from its star. If this orbit were placed within our solar system, it would pass through a region closer to the Sun than Mercury. This comparison only helps us picture the distance, since conditions around a star also depend on its brightness, temperature, and many other characteristics. Even so, it reveals just how deeply this world has entered the region of intense radiation. The phrase "plunging into fire" does not mean that flames from the star are reaching across space and touching the planet. Between the two bodies lies an almost empty vacuum. What carries heat across that distance is radiation. Visible light, infrared radiation, and other forms of energy leaving the star, crossing space, and being absorbed by the upper layers of the atmosphere. A planet does not need to touch a flame to be heated. When countless photons enter the atmosphere, they transfer energy to molecules, strengthening the motion within the material. Molecules vibrate, rotate, and collide more rapidly, causing temperatures to rise, gases to expand, and pressures to begin changing. The process unfolds in silence, but its effects can spread across an entire world. In the distant part of the orbit, the atmosphere once had enough time to absorb heat, transport it, and radiate some of it back into space. Near Periastron, the incoming energy rises so rapidly that this balance can no longer be maintained. The system resembles a room being heated, but before the air, walls, and furniture can adjust to the current temperature, someone turns the thermostat higher again. The room is always one step behind the heat source. This is what happens on HD 80606b while the planet is also moving at its greatest speed. It does not remain beside the star long enough to settle gradually into a stable hot state. Its orbit carries it past the closest region at tremendous velocity, delivering a powerful burst of energy before almost immediately beginning to move away again. This combination of intensity and brief duration is what makes the encounter so unusual. The atmosphere is heated rapidly, but it does not have enough time to respond evenly. Recent observations with the James Webb Space Telescope show that the temperature in the measurable part of the atmosphere rose by more than 600 degrees Celsius as the planet passed through the region near its star. This is not the temperature of the entire world, nor does it mean every atmospheric layer warmed by the same amount at the same moment. The telescope mainly tracks infrared radiation emerging from the layers of gas whose light can carry information to us. Even so, the increase is enough to reveal one of the fastest thermal changes ever monitored on an exoplanet. On Earth, the transition from morning to noon may raise the temperature by only a few degrees, yet the human body can easily feel the difference. On this world, hundreds of degrees can be added to part of the atmosphere over a similar span of time. There is no ground where a person could stand, no breathable air, and no environment resembling life as we know it. But comparing the timescales helps us understand the scale of the change. This is not a trend unfolding over centuries. It is planetary weather transforming almost before the eyes of our telescopes. The incoming heat first acts most strongly upon the region facing the star. There, the atmospheric layers receive direct radiation and begin warming first. Areas farther from the point of strongest illumination retain their previous conditions for longer, while deeper layers respond more slowly because of their greater mass and stronger thermal inertia. At the same moment, one part of the planet has already entered a new state, while another still carries traces of the quiet interval that came before. This contrast immediately drives motion. Hot gas expands, pressure changes, and winds begin carrying energy toward the surrounding regions. Yet heat cannot be transported as quickly as the source of light is changing. While the winds are still redistributing energy received several hours earlier, the planet has already reached a new point in its orbit, where the incoming radiation is different once again. The process can be pictured as a drop of ink released into flowing water. The ink begins spreading as soon as it touches the water, but before the color can become evenly distributed, the current has carried the entire mixture somewhere else. Heat behaves in much the same way on this planet. It does not remain fixed where the radiation was first absorbed, but neither can it spread quickly enough to bring the entire atmosphere into the same state. Seen in infrared light, the world would probably not appear as a sphere brightening evenly all at once. One hot region would stand out first, then shift and change shape as winds carried energy away. Atmospheric layers at different altitudes might also respond at different times. Scientists cannot record a sharply detailed movie of this process, but tiny changes in the light from the entire system allow them to reconstruct the rhythm of the planet's heating and cooling. Then the moment of closest approach passes. The orbit carries the giant gaseous world around the star and begins opening outward again. The distance increases, and the stream of radiation gradually weakens, but the atmosphere does not immediately return to its former state. The heat it has just absorbed remains within the layers of gas. Winds continue transporting it, and chemical reactions set in motion during the encounter may continue even as the light begins to fade. The planet is like someone who has just passed in front of an open furnace. It may take only a few seconds to cross the hottest region, but the warmth remains on the skin and clothing long after the furnace door has been left behind. On a vastly greater scale, the atmosphere carries the after effects of its close approach, continuing to change even as the world moves away from the region nearest the star. The hours beside the furnace are therefore not an event with clearly defined boundaries. The heating begins before periastron, reaches its greatest intensity around the close approach, and continues spreading through the atmosphere after the planet has already begun to retreat. One part of the world is moving away from the strongest light, while another is only beginning to feel the full effect of the energy that has just been delivered. From hundreds of light years away, all of this appears only as a subtle change in infrared radiation, yet hidden within that faint signal is an immense atmosphere struggling to adjust to a shift occurring faster than its own natural rhythm. The close encounter is over. The planet has not been swallowed, nor has it burned to ashes. Its velocity has carried it to the other side of the orbit, where the star will gradually appear smaller again. But the world leaving the hottest region is no longer the same world that entered it. The upper layers of gas have absorbed an enormous amount of energy, the temperature differences between regions have deepened, and the entire atmosphere is now struggling to catch up with an encounter that has already begun to recede into the distance. The point of closest approach now lies behind the planet, but for the atmosphere, the encounter is not truly over. The distance is increasing again, the bright disk of the star is beginning to shrink, and the stream of energy pouring onto the planet is no longer as intense as it was only a few hours ago. Yet the layers of gas that were just heated are still expanding. New regions of pressure are still forming, and the immense amount of energy recently absorbed cannot immediately disappear into space. The orbit has moved on, but the atmosphere remains within the afterglow of the encounter. This is what makes HD 80606b more fascinating than a world that is simply very hot. Its temperature does not entirely reflect where the planet is at the present moment. It also carries traces of the places it has just passed through. As it approaches the star, the layers of gas do not heat up instantly, and as it begins moving away, they do not cool at once. The entire planet behaves like an immense body, responding more slowly than the changes unfolding around it. We can feel something similar in a room just after the heater has been turned off. The heat source has fallen silent, but the walls remain warm. The floor still holds its heat, and the blanket continues to carry the comfort of a few moments earlier. The room does not instantly become cold simply because the switch has changed position. Matter needs time to release the energy it has absorbed. On this giant gaseous planet, that delay extends through an atmosphere deeper and broader than any room we could imagine. The upper layers, where the gas is thin and starlight can reach more easily, respond first. They heat rapidly, expand, and begin emitting more infrared radiation. But far below, the denser layers still follow the slower rhythm of the distant part of the orbit. They have not yet absorbed the full force of the new heating, even as the regions above have already begun entering a different state. For this reason, the same world can contain several moments within its atmosphere. In one place, molecules are reacting to the powerful radiation that has just arrived. Somewhere else, the gas still carries the temperature of earlier hours. Deeper still, part of the planet has barely registered that the close approach occurred at all. The past does not disappear when the present arrives. The two states overlap, preserved within layers of matter that respond at different speeds. The source of light changes according to the rhythm of the orbit, while the atmosphere changes according to its own. Near periastron, the planet sweeps through space very quickly. Within a brief interval, the amount of energy it receives rises dramatically and then begins to fall. But the gas cannot instantly absorb, distribute, and release all of that energy. It is like a large wave that has already crossed the shoreline, while the water is still rising between the rocks and continuing to flow farther inland. This delay is not a sign that the atmosphere functions inefficiently. It is the natural result of a system so immense. Heating such a vast amount of matter takes time, and transporting that heat from one region to another takes even longer. Even if the winds move at tremendous speeds, they must still cross a world nearly the size of Jupiter. While they are carrying energy across the planet, the external heat source has already continued to change. The region facing the star receives the burst of heating first. The gas there expands, pressure shifts, and the atmosphere begins pressing into neighboring regions. From this point, heat is no longer merely a number. It becomes motion. Vast currents of gas form, carrying energy away from the hottest region and toward areas that have not yet had time to respond. But an atmosphere does not transport heat as neatly as someone pouring water from one glass into another. Currents of gas may twist, change direction, overlap with motions that already existed, and pass through layers of different densities. While one region is heating, another may already be cooling. Between them, the winds continue carrying the energy of hours that have passed. There is no clean boundary between the hotter and less heated regions, only transitional zones whose shapes are constantly changing. If we could see the planet with eyes sensitive to infrared light, we probably would not observe a uniformly glowing sphere. A hot region might appear first, then shift away from the area receiving direct starlight as the winds carried its energy elsewhere. Its shape might stretch, distort, or spread into other regions, while the upper and lower atmospheric layers glowed according to rhythms that were not entirely the same. This is not yet a movie that human beings can watch directly. The planet is too distant and lies too close to the overwhelming glare of its star for telescopes to resolve individual clouds. All we receive is a very small change in the total radiation coming from the entire system. Yet by following that signal over time, scientists can determine when the world begins to warm, when it reaches its greatest infrared brightness, and how long it takes for the heat to start fading. The delay between the strongest starlight and the highest temperature is especially valuable. It reveals how long the atmosphere retains heat and how quickly it transports energy. If the hot region reaches its peak almost immediately as the planet passes closest to the star, the observed layers may be responding very quickly. If the thermal peak arrives later, it suggests that energy is being stored or continuing to spread through the atmosphere after the strongest radiation has already passed. Something similar happens on Earth, though in a much gentler form. The hottest part of the day usually does not occur at the exact moment when the sun is highest in the sky. The ground and air continue absorbing energy for some time before the amount of heat being lost becomes greater than the amount being received. The ocean also warms and cools more slowly than the land because a large body of water can retain energy for longer. These familiar effects are small versions of the same principle operating on this distant world. HD 8, 0606b, however, does not have only a surface or an ocean that responds slowly. Nearly everything we can observe is gas, and beneath it lie layers of matter that become increasingly dense and increasingly resistant to rapid change. There is therefore no single temperature that represents the entire planet. When a telescope measures a temperature, it is listening to the voice of particular atmospheric layers at a particular wavelength and at a particular moment. One wavelength may carry information from high in the atmosphere, where the gas responds quickly to starlight. Another may emerge from deeper regions, where heat is retained for longer. By combining these signals, astronomers can learn not only how hot the planet becomes, but also begin to picture the depth of its atmosphere and the direction in which energy is moving through it. In a beautiful sense, the delay itself helps this world reveal its structure. If every layer of gas heated and cooled in the same instant, we would see only a simple signal. But because each layer responds according to a different rhythm, the infrared light carries more traces within it, traces of depth, of heat retention, and of the motions unfolding inside the atmosphere. Meanwhile, the planet continues moving outward. The radiation from the star grows weaker, but the hot region created during the close approach may still be drifting through the atmosphere. Winds carry it away from its original location, so the hottest place does not necessarily remain directly beneath the point receiving the strongest light. The heat source has begun to recede, but its imprint is being carried around the world. This makes the atmosphere resemble a river carrying the color of the land it has just passed through. Even after leaving the place where the water was most deeply stained, the current continues carrying that color for a long distance. Only as it is diluted, dispersed, and gradually released does the trace begin to fade. HD 80606b will also cool again. The upper layers will radiate energy into space, temperature differences will diminish, and atmospheric motion may gradually become more stable as the planet continues moving away from the star. But the process is not rapid, nor does it unfold evenly. Some regions have already begun to soften, while others are still receiving heat carried by the winds. The close approach is over according to the orbital clock, but within the atmosphere, it continues in another form. That is why this planet resembles such a remarkable natural experiment. Every 111 days, the same atmosphere is carried from a region of weaker heating into a powerful burst of radiation and then rapidly drawn outward again. Scientists can watch it warm, measure the delay, and follow the way it radiates heat as it retreats. Nature repeats the experiment on its own, not inside a laboratory on Earth, but on the scale of an entire world. Even now, the atmosphere has not yet caught up with the planet's new position. The star has grown smaller, but the heat is still spreading through the layers of gas. The past is being carried by the winds from one region to another, while the entire world slowly finds its way back toward a quieter state. And as the heat begins to move, another story comes into view. Energy cannot spread across a giant gaseous planet without creating vast currents of motion. The difference between the regions that were just intensely heated and those that remain cooler will drive the atmosphere forward, bend the winds, and perhaps form structures extending around the entire world. The close approach has given the atmosphere an immense amount of heat. What follows is the way it transforms that energy into weather. The close approach has delivered an immense amount of heat to the atmosphere, but that heat cannot remain still where it was absorbed. As soon as one region of gas becomes much hotter than the areas around it, the old balance begins to break down. The gas expands, pressure changes, and the entire atmosphere is driven into motion. From those differences, vast winds begin to form across a world with no solid ground to slow them down. On Earth, winds often arise when air moves from regions of high pressure toward regions of lower pressure. The sun heats the land and oceans unevenly, causing the air above them to receive different amounts of energy. Warmer air is lighter and tends to rise, while cooler air moves in to replace it. From motions that seem so simple, larger weather systems gradually take shape. On this giant gaseous planet, the basic principle remains the same. but the scale and conditions are entirely different. There are no continents that absorb sunlight during the day and cool rapidly at night. There are no mountains to redirect the flow of air, no forests to create friction, and no coastlines dividing land from water. The atmosphere extends continuously around the entire world, and beneath the layers we can observe lie deeper and increasingly dense regions of gas. When the side facing the star is heated rapidly, the gas there expands and creates a pressure difference between that region and areas that have received less energy. Heat then begins to move away. Currents of gas flow out of the hot region toward cooler areas, while material from elsewhere moves in to replace them. If the planet were smaller and the heat source changed slowly, this process might gradually settle into a relatively stable pattern of circulation. But here, everything is unfolding, while both the incoming light and the planet's position are changing rapidly. The hottest region does not remain still long enough for the atmosphere to reorganize itself easily. While the first winds are still carrying heat away, the planet has already moved farther along its orbit. The intensity of the radiation begins to fall, the angle of illumination changes, and the atmospheric layers continue to carry energy absorbed several hours earlier. The weather therefore responds not only to where the star is in the sky, but also to the history of the close encounter that has just taken place. We might imagine the atmosphere as a broad sheet of fabric being pulled sharply at one point. The place where it is pulled does not remain fixed, but keeps moving. Folds appear, spread outward, overlap, and change as the force itself shifts. On this planet, those folds are regions of pressure, currents of heated gas, and patterns of motion stretching across a large portion of the world. The winds, however, do not necessarily move in a straight line from the hottest region toward the coolest. The planet is still rotating, and that rotation deflects the currents away from their simplest path. On Earth, a similar effect helps curve atmospheric flows and shape rotating storms. On a larger world, with faster winds and a deeper atmospheric structure, that deflection may create long bands of motion, enormous vortices, or currents flowing around the entire planet. We have not observed those winds directly. No probe is drifting through the atmosphere and returning images of individual clouds, and telescopes cannot yet resolve the cloud tops into clear detail. Most of what scientists know comes from infrared light, from the timing of the planet's heating and cooling, and from computer models built upon established laws of physics. In those models, the atmosphere is divided into many layers and regions. Researchers include the energy arriving from the star, the planet's mass, gravity, rotation rate, and the ability of the gas to absorb radiation. They then allow the system to evolve over time to see where the heat travels, how quickly the winds accelerate, and how the hot region shifts. The results often suggest that atmospheric currents may reach tremendous speeds, enough to transport heat across thousands of kilometers within a short period. Some models also indicate that the rapid changes around periastron could produce powerful wave-like structures in the atmosphere, where moving currents meet or become compressed. These features are sometimes described with terms such as shock waves or global storms, but those descriptions need to be understood carefully. A storm on Earth brings to mind dark clouds, heavy rain, and winds striking the ground. On this world, a storm may simply refer to a system of motion on a planetary scale, without rain, lightning, or any structure resembling the storms we know. The atmospheric composition is different, the temperatures are different, and there is no solid surface. So even when the gas currents are extremely powerful, the physical experience would be entirely unfamiliar. The absence of solid ground does not mean that the winds can move freely forever without resistance. Atmospheric layers still rub against one another, exchange momentum, and create turbulent regions. Deeper below, pressure rises, matter becomes denser, and motion may carry energy into lower layers. The atmosphere is therefore not a thin shell sliding across a sphere, but a deep body of fluid in which currents near the top may be connected to movements far below the limits of observation. This makes every wind part of a much larger system, A current of hot gas leaving the recently illuminated region may draw material upward from below. A cooler region sinking downward may carry energy deeper into the planet. These motions overlap with convective currents that were already present, so the atmosphere does not begin from an empty or motionless state each time the planet approaches its star. The close encounter simply adds a powerful new rhythm to a system that was already in motion. If we could hover above the cloud tops and look down, we might not see a scene of constant chaos. On very large scales, many movements could appear slow and graceful, even if the gas itself were traveling at tremendous speed. Cloud bands might stretch across the curve of the planet. Bright infrared regions might drift away from the place receiving direct heat, and vortices thousands of kilometers wide could take hours or days to change shape noticeably. This is one of the beautiful paradoxes of scale. A wind may be stronger than any storm humanity has ever experienced, yet from a distance it appears only as a gentle shift in light. A weather system may cover half the planet, while through a telescope it reveals itself as nothing more than a subtle change in the brightness of a faint point beside the star. Those slight changes allow scientists to test their models. If the hot region shifts quickly, the peak in infrared brightness will appear at a different time. If the winds transport heat efficiently, the contrast between warmer and cooler regions will be reduced. If the atmosphere retains energy for a long time, the planet will continue glowing strongly even after it has moved away from periastron. Every detail in the light curve is a trace of motion that the human eye cannot observe directly. In the hours after the close approach, the atmosphere resembles a system that has just received a powerful push and is now trying to recover its rhythm. The winds do more than transport heat. They also change the altitude of atmospheric layers, bring regions with different chemical compositions together, and may cause clouds to form or disappear in new locations. Heat, motion, and atmospheric chemistry begin to interact, turning the weather into something more than a simple story of warming and cooling. Gradually, as the planet continues moving away, the incoming radiation weakens, and the largest contrasts begin to diminish. The winds continue their work, but they are no longer being driven by a heat source that is rapidly intensifying. Hot regions radiate some of their energy away, broad currents spread outward and begin to slow, and the atmosphere moves step by step toward a less violent state. But it does not return to precisely what it was before. Each close approach may leave temporary traces in the distribution of heat, the locations of hot regions, and the chemical reactions that were set in motion. The planet emerges from the fiery region with an atmosphere that has been thoroughly stirred, like water that continues to ripple long after the stone has disappeared beneath the surface. The winds on this world without solid ground are therefore more than a consequence of heat. They are the planet's way of responding to extreme differences, carrying energy away from the hottest regions and dispersing it across a wider expanse. Although they cannot restore balance immediately, they prevent the heat from remaining entirely concentrated in one place, transforming a brief shock into a process that is longer, gentler, and more widely distributed. The orbit created the sudden rise in temperature. That rise produced pressure differences. Those differences gave birth to winds, and the winds began to redraw the thermal map of the entire planet. After all these changes, we can begin to see this world in another way. Rather than imagining a single planet whose weather simply changes over time, we might picture it as alternating between two distinct faces. Far from the star, the atmosphere is relatively stable and less affected by extreme heating. But when the planet plunges into the region near periastron, that same atmosphere becomes an environment violently stirred by an enormous influx of energy. The contrast between these two phases reveals how, within a single short orbit, one planet can pass through conditions so different that they almost seem to belong to two separate worlds. The planet is still moving away from its star, but the close encounter has not completely left the planet behind. In the upper atmosphere, winds continue carrying heat away from the region that received the most intense radiation. Farther below, dense layers of matter still retain energy they have not yet had time to release. The bright disk in the sky has begun to shrink, but the atmosphere cannot instantly forget the hours it has just endured. It carries the encounter with it, like a room whose walls and floor remain warm long after the heater has been turned off. Looking back across the entire orbit, we begin to see that HD 80606b is not a world with only one clearly defined climate state. It spends most of its short year in the distant region, where the star appears smaller, the light changes more slowly, and the atmosphere has time to gradually radiate some of its heat into space. Then the orbit pulls it inward again. Its speed rises, the light intensifies, and its relative stability gives way to a burst of heating so rapid that the atmospheric layers cannot respond together. If we could observe the planet only at the far end of its orbit, we might imagine a giant gaseous world passing through a relatively quiet interval. Heat would still rise from deep inside, winds would still move through the cloud layers, and the atmosphere would never be completely still. But the surrounding environment would not be changing faster than the planet could adjust. The world would have time to breathe according to a longer rhythm, to soften the remaining contrasts, and to gradually return to a less intensely heated state. If we saw it only during the hours nearest the star, the image would be almost the opposite. The stellar disk would expand across the sky. The incoming radiation would rise sharply, and the upper atmosphere would heat first, while the deeper regions continued to carry traces of the old state. Temperature differences would create pressure differences, winds would begin moving energy across the planet, and the hottest region would continuously change shape as the orbit carried the entire world forward. These two moments are so different that we might believe we were observing two separate planets. One world with time to settle beneath weaker light, and another being drawn into a region of intense radiation, where temperatures rise by hundreds of degrees within only a few hours. But what gives the story greater depth is that there are not two planets here. There is only one world, with one atmosphere, repeatedly carried through nearly opposite conditions, and then bringing traces of each one into the next part of its orbit. As the planet leaves the distant region, it does not completely abandon its quieter state. The deeper atmospheric layers still respond slowly, currents formed earlier continue moving, and the internal heat cannot vanish simply because the distance is shrinking. As the planet passes closest to the star, the upper atmosphere enters a new state first, while beneath it remains a world that has not yet fully caught up. And when the planet begins moving outward again, the process reverses. The light weakens first, while heat continues spreading through the atmosphere and winds keep distributing energy received during the preceding hours. HD 80606b therefore exists almost constantly within an overlap. Part of the atmosphere is responding to the present, another part is preserving the past, and deeper layers may not yet have fully experienced the change that has already passed. The orbit has moved into a new position, but temperature, winds, and atmospheric structure cannot all move with it at once. This delay prevents the planet from crossing from one state to another along a clear boundary. Instead, it drifts through a long transitional region where the two faces of the same world blend together. If every atmospheric layer changed instantly, this planet would probably reveal far less. The light would increase and the temperature would rise with it. The light would fade and the temperature would immediately fall. The entire story would become a simple line of response. But because the atmosphere needs time to absorb, transport, and release energy, each phase leaves behind a delay. Within that delay, astronomers can find traces of the structure beneath. A layer that responds quickly may be relatively thin or especially efficient at absorbing energy. A hot region that continues brightening after the planet has moved beyond its closest point suggests that heat is being retained or carried somewhere else. If the hottest region shifts away from the area receiving direct illumination, it may be evidence that winds are transporting energy around the world. By following the timing of each change, scientists can learn not only how hot the planet becomes, but also how that heating unfolds. This is what turns the 111-day orbit into such a rare natural experiment. During every revolution, the same atmosphere is carried from a region of weaker heating into intense radiation, then rapidly drawn away again before it can reach complete equilibrium. There is no need to compare two planets with different masses, ages, or compositions. Nature places the same world into several environments in succession, then repeats the process regularly enough for telescopes to follow. From Earth, no one can see these two faces as clearly defined globes beside one another. The planet is too distant, and the star's light is too overwhelming for individual cloud bands to appear in a direct image. All that reaches us is a tiny variation in the total infrared light from the system. Yet when that faint signal is followed over many hours, it gradually becomes a line of narration. The brightness rises as the atmosphere warms, reaches a peak after a delay, and then slowly fades as the world continues moving outward. At the beginning of the journey, the central question was how a planet could move from a relatively quiet state into a temperature rise of hundreds of degrees within such a short time. By now, the answer has begun to emerge. The elongated orbit carries this world from a distance roughly comparable to that between Earth and the Sun into a region much closer to its star. Gravity accelerates the planet. The shrinking distance causes the incoming energy to increase dramatically, and the atmosphere is too deep and massive to respond evenly to such a rapid change. But understanding light, temperature, and wind reveals only how the planet transports energy. Within those moving currents is matter, atoms and molecules, compounds that may remain stable at one temperature but become difficult to sustain at another, and tiny particles that may condense into clouds before disappearing again as the environment grows hotter. And just as temperature cannot instantly keep pace with the orbit, the chemistry of the atmosphere may respond more slowly than the changes unfolding around it. A molecule formed in the less intensely heated region may be carried by winds into hotter air before it has time to transform. A gas suited to high temperatures may remain present even after the planet has begun to cool. Cloud layers that once concealed the atmosphere below may thin or evaporate during the close approach, then require additional time to return as the world moves outward. This means that the planet's two faces may differ not only in brightness, temperature, or the strength of their winds. They may also differ in the very composition detected by telescopes, in the altitude from which light can escape, and in the cloud layers that hide or reveal the atmosphere beneath. Each passage through the fiery region may do more than stir the atmosphere. It may also rearrange the matter within it. The next question, then, is no longer simply how hot the planet becomes. What is more intriguing is whether, when an entire atmosphere is carried through two nearly opposite conditions during a single orbit, its molecules can change quickly enough to follow the temperature, or whether they continue carrying the memory of the state that came before. One orbit has created two faces of the same world. Now, among the atmospheric layers still moving after the close encounter, chemistry may be preserving a subtler story, one in which the past remains not only in the heat, but also in the way matter itself is arranged. The heat of the close approach remains not only in the winds and in the regions of gas that are slowly cooling. It also reaches into a less visible layer, where countless molecules are constantly colliding, breaking apart, and combining in new ways. There, weather does more than change the temperature of the atmosphere. It may also alter the composition the atmosphere reveals to the outside. Each kind of molecule is better suited to certain conditions. Temperature, pressure, and gas density determine which bonds remain stable, which reactions proceed quickly, and which compounds become more abundant. When the planet is in the distant part of its orbit, the upper atmosphere has more time to move toward a state suited to weaker heating. But as the distance to the star shrinks and temperatures rise sharply within a few hours, that arrangement is pushed into an entirely different environment. Chemistry does not respond the instant the light changes. Some processes may unfold quickly, while others require more time than the close approach allows. As a result, the atmosphere does not immediately become a perfect mixture corresponding to its new temperature. The planet may already have entered the hotter region, while its molecules still carry a state formed during the days spent farther away. It is somewhat like a large pot of water. After the heat has suddenly been turned up, the water near the bottom receives energy first, and convection begins carrying warmer water upward. But the entire pot does not reach a new temperature at the same moment. If it contains many different components, each one will also respond at its own pace. For a while, the old state and the new state coexist, blending together before a clear equilibrium can form. The atmosphere of HD 80606b is even more complex because the differences are not limited to high and deep layers. The winds created after the sudden heating continuously carry matter through regions with very different conditions. A molecule formed in a hot region may be swept into cooler air before it has time to change. Conversely, a compound created in a less intensely heated region may be drawn into stronger light and continue to survive for some time, even though the new environment is no longer favorable to it. When the composition of a gas has not yet fully adjusted to the current temperature and pressure, scientists call it chemical disequilibrium. The term may sound complicated, but the idea is simple. The atmosphere still carries a memory of where its material used to be. What telescopes observe reflects not only the present, but also traces of the past and of the journey the winds have carried those molecules through. Chemistry can therefore become an indirect way of tracing motion through the atmosphere. If a compound appears in a region where the current temperature should not favor it, that material may have arrived from somewhere else. If a molecule remains long after the planet has moved away from its closest point, the reaction that transforms it may be proceeding more slowly than the atmosphere is cooling. Every small mismatch between temperature and composition reveals something about how the atmosphere works. These molecules cannot be sampled directly. No instrument is drifting through the cloud layers, collecting gas and sending it back to Earth. Instead, we read the traces they leave in light. Each kind of molecule absorbs certain characteristic wavelengths, producing small dark gaps in a spectrum. When the planet's infrared light is separated into different regions of color, those absorption features can reveal which substances may be present. This work is far more delicate than simply looking at a bright line and naming a compound. The temperature of each atmospheric layer can strengthen or weaken the signal. Clouds may hide deeper regions. Different molecules can leave features close together, causing their signals to overlap. And because the planet does not appear as a clearly resolved disk, telescopes usually receive blended light from many parts of the atmosphere at once. Among the substances of interest are carbon-bearing molecules such as methane, carbon monoxide, and carbon dioxide. Their relative amounts can change with temperature, pressure, and reaction speed. Under milder conditions, methane may be more favorable. As the gas grows hotter, carbon monoxide may become more dominant. Yet powerful winds and the rapid orbital changes may prevent the atmosphere from reaching such a simple equilibrium, causing these molecules to appear in ways that differ from what equilibrium models predict. What matters is not merely whether a particular gas is detected. The greater value lies in seeing whether the chemical signatures change over time. If the spectrum before the close approach differs from the spectrum afterward, that difference may show how deeply the heating altered the atmosphere. If some features remain after the planet has moved away from the star, they may suggest that the chemistry responds slowly or that winds are strongly mixing material between atmospheric layers. The James Webb Space Telescope can track these subtle changes in infrared light, but interpreting the data still requires great care. New observations offer an opportunity to study the atmosphere's composition as the planet heats and cools, yet this does not mean every molecule has been identified with certainty or that the entire chemical process is fully understood. The signals must still be compared with many different models, because temperature, clouds, and atmospheric motion can all reshape the spectrum. That uncertainty does not make the story any less compelling. It shows that we are observing an atmosphere, while it is truly changing, rather than seeing only a state that has remained stable for a very long time. Each time the planet passes close to its star, temperatures rise, winds strengthen, and chemical reactions may shift into a different rhythm. As the world moves away, conditions become gentler, but the composition does not necessarily return to its former state at once. Chemistry has its own form of inertia. For this reason, a 111-day orbit may not be a perfectly simple repetition. The planet follows the same path, but its atmosphere may enter each close approach with heat patterns, winds, and chemical compositions that are not arranged exactly as they were during the previous orbit. Some traces from the earlier cycle may still remain when the next one begins, blending with the new changes being created. From hundreds of light years away, these details appear only as a few subtle shifts in light. Yet within them lies a story of matter being carried through hotter and less intensely heated regions, of molecules unable to adjust in time, and of an atmosphere preserving the past not only through its warmth, but through its very composition. That chemistry may eventually lead to a change that is easier to picture. As temperatures fall, some materials may condense into tiny particles suspended in the gas. When the planet approaches the star again, those particles may heat up, evaporate, and gradually reveal deeper layers below. Along with invisible molecules, clouds may therefore appear and disappear to the rhythm of the orbit, changing the appearance of the atmosphere after each journey through the fiery region. As the planet continues moving away from its star, the heat in the upper atmosphere begins to ease, more slowly than the orbit itself changes, but enough to open the way for something new. Molecules that once existed as gases may again encounter conditions that allow them to condense into tiny particles, suspended in the atmosphere like a thin veil of mist, slowly being woven back together after the close approach. On a world with no oceans, no continents, and no sky in the familiar sense, clouds can still appear. But they are not necessarily made of water, nor do they take any shape the human eye has ever known. What defines a cloud is not its white color or its ability to produce rain, but the moment when a substance changes from a gas into countless tiny particles drifting through an atmosphere. On Earth, that substance is usually water. On far hotter planets, clouds may be made from entirely unfamiliar compounds, including materials that, under ordinary conditions on our world, exist only as rocks or minerals. In an atmosphere hot enough, they can vaporize. When they enter cooler regions, they condense again into fine particles and begin to obscure the layers of gas below. In the distant part of its orbit, HD 80606b receives less energy from its star, so some regions of the atmosphere may become more favorable for condensation. The entire planet does not suddenly become covered by one uniform layer of cloud. Temperature varies with altitude, location, and the way winds transport heat, so clouds may form first in one region, remain thinner in another, and then stretch into broad bands around the world. From such a great distance, none of these motions can be seen directly, but they may alter the amount of light and heat escaping from the atmosphere. A thick cloud layer is like a curtain drawn across a room with a light shining behind it. The room is still there, and the source of light remains, but an observer outside can no longer see the interior in the same way. On this giant gaseous planet, the deeper layers may be hot and emit large amounts of infrared radiation, but if a sufficiently dense cloud deck forms above them, some of that energy will be hidden or altered before it can escape into space. For this reason, when a telescope sees the planet becoming brighter or dimmer at a particular wavelength, temperature may not be the only cause. The atmosphere below may have grown hotter, but the upper cloud curtain may also have thinned, allowing us to see deeper into layers that were previously concealed. Conversely, when clouds become thicker, a chemical signature may appear weaker even though the molecule producing it is still present below. This is one of the great challenges of interpreting light from a distant world. A telescope does not receive a clear image of each individual cloud layer. it collects a combined signal from the entire planet. Within that signal, temperature, atmospheric composition, and clouds are blended together. A small change may have several possible explanations, and scientists must compare each one with atmospheric models to find the interpretation that fits best. The journey toward the star causes this curtain to change more rapidly. As the light intensifies and the upper atmosphere is heated, particles that remain stable during the distant phase may begin to evaporate. The cloud layer does not necessarily vanish across the entire planet at once. Regions receiving more radiation will change first, while cooler areas may retain their clouds for longer. Winds then carry those particles through regions with different temperatures, allowing them to form, evaporate, and condense again somewhere else. The process resembles mist on a window in the morning. Where the glass remains cool, its surface stays hazy with tiny droplets of water. When sunlight reaches it, the mist begins to retreat, but not evenly. Some areas become clear first, while others remain clouded for longer. On HD 80606b, this does not happen across a small pane of glass, but throughout an immense atmosphere, with materials unlike water and winds capable of carrying them across thousands of kilometers. As the planet approaches periastron, the heat may cause some clouds to disappear quickly enough to expose deeper atmospheric layers. Telescopes would then receive radiation from regions that were previously hidden, making the world appear brighter in certain infrared wavelengths. Even then, however, we should not imagine the atmosphere becoming completely transparent. Some cloud layers may remain at other altitudes. Certain regions may stay cooler, and tiny particles carried by the winds may continue forming uneven veils of haze. Clouds are not merely passive screens. They can also influence the temperature of the atmosphere itself. Highly reflective particles may send some of the incoming starlight back into space, allowing the layers below to absorb less energy. In other cases, clouds may trap infrared radiation that is trying to escape, slowing the cooling process. Their actual effect depends on their composition, particle size, altitude, and the wavelength of the light. The same cloud layer may cool one part of the atmosphere, while helping another retain heat. On a planet with a nearly circular orbit, a cloud system may have time to approach a relatively stable state. HD 80606b gives its atmosphere no such regularity. In the distant region, new particles may begin to condense. As the planet accelerates inward, the conditions that allowed them to form quickly disappear. During the hours nearest the star, part of the curtain may thin or be drawn aside. Then, as the world moves outward and gradually cools, the process of weaving it together begins again. But the new curtain may not be exactly the same as the old one. Winds have moved material to different places, atmospheric regions have passed through different temperatures, and some chemical reactions may not yet have returned to their earlier state. Each passage through the fiery region may therefore leave behind a slightly different cloud structure, at least for a time, before the atmosphere gradually settles into a steadier rhythm. This is also why clouds are an important part of the planet's climate story. They reveal not only where conditions are cool enough for matter to condense, but also influence what telescopes can see, how heat is retained, and how light travels through the atmospheric layers. A changing cloud deck can reshape the spectrum, making a molecule appear more or less prominent, even when the actual gas composition has not changed nearly as much. Much of this picture is still built from models and indirect traces in the light. No probe has entered the atmosphere to photograph individual cloud bands, and no telescope has yet seen the planet as a sharply resolved globe with visible weather patterns. What we have are temperatures changing over time, spectra measured across many wavelengths, and models showing where materials may condense or under what conditions they may evaporate. The absence of direct images does not make these clouds any less real. On the contrary, the changing light reveals that the atmosphere is not a uniform, motionless layer of gas. It is hiding and revealing different depths, carrying matter from one region to another, and changing during the very hours in which telescopes are watching. As the planet continues moving outward, the upper atmosphere gradually becomes gentler. Wherever the temperature falls low enough, new particles may begin to appear, sparse at first, then growing more abundant as conditions become favorable. The atmosphere slowly closes the transparent openings created during the close approach, as though a curtain pulled aside by the heat were gradually being lowered once again. And as that curtain enters the story, another question becomes difficult to avoid. If the planet is too distant for us to see individual clouds, and its light is millions of times fainter than its star, how do we know this world exists at all? How do we know how massive it is, or that its orbit is stretched into such an unusual shape? The answer does not begin with seeing the planet. It begins with watching the star very carefully, where a tiny motion hidden within its light revealed the presence of a giant world pulling the star back and forth with every orbit. The story of HD 80606b did not begin with a photograph of the planet. No one saw it emerge as a separate sphere beside its star, and no telescope ever captured a single image of its unfamiliar cloud layers or its elongated orbit. The first thing humanity noticed was only a tiny change in the star's light, so subtle that without sensitive instruments and observations extending over long periods, it could easily have been dismissed as an insignificant variation. The star HD 80606 is vastly brighter than its planet. Seen from Earth, the planet's light is almost completely lost within the glare of its parent star. The apparent distance between the two objects in the sky was also too small for the telescopes of the time to separate them into distinct points. So astronomers did not search for the planet by looking directly at where it was. They watched the star and waited to see whether its light would reveal any hidden motion. A planet, even though it is far smaller than its star, still has gravity. It is not merely pulled along its orbit by the star, it also pulls the star in the opposite direction. The two objects actually move around a shared point, known as the center of mass. When one object is a massive star and the other is a much lighter planet, that point usually lies deep inside the star. So the star's movement is only a slight wobble. But if the planet is massive enough and its orbit unusual enough, that wobble can leave a detectable trace in the light. One simple way to picture this is to imagine two people holding hands and spinning around together. The lighter person must travel in a wide circle, while the heavier person only leans and turns around a much smaller region. Although they cover different distances, both are rotating around a point between them. In the HD 80606 system, the planet follows its broad, elongated orbit, while the star responds with a much smaller motion, sometimes shifting slightly toward Earth and sometimes moving away. Human beings cannot see that displacement directly. The star is far too distant for telescopes to record it visibly swaying back and forth across the sky. Instead, astronomers detect the motion through the way its light changes as the source moves toward or away from the observer. This is the Doppler effect, a phenomenon more familiar than it may seem. As an ambulance approaches, its siren sounds higher in pitch. After it passes and begins moving away, the sound drops lower. The siren itself has not changed, but the sound waves are compressed as the source approaches and stretched as it retreats. Light can carry a similar signature, even though the human eye cannot detect it through ordinary vision. When the star moves slightly toward Earth, the characteristic lines in its spectrum shift toward shorter wavelengths. When the star moves away, those lines shift toward longer wavelengths. The change is far too small to make the star visibly change color. It appears only when the light is separated into a spectrum, and the positions of individual lines are measured with extraordinary precision. Each spectral line acts like a marker. These lines are produced by elements in the star's atmosphere, and under stable conditions, their positions can be predicted with considerable accuracy. If the entire group of lines shifts in one direction and then, after some time, moves back the other way, it indicates that the star is moving toward and away from us in a repeating cycle. In the early 2000s, as the light from HD 80606 was monitored across many observations, astronomers found that the star's velocity did not remain constant. It changed in a repeating rhythm, but the pattern was not smooth and even like the signal produced by a planet in a nearly circular orbit. During some intervals, the change was slow. Then, within a much shorter period, the star's velocity shifted far more dramatically. That unusual shape was the first indication that the unseen object pulling on the star was following a highly elongated orbit. From those data, scientists learned more than simply the existence of a planet. They began reconstructing its motion. The time required for the signal to repeat revealed an orbital period of about 111 days. The size of the star's wobble provided information about the mass of the object pulling it. And the uneven rise and fall of the measured velocity showed that the planet was not traveling along a nearly circular path, but spending most of its time far away before accelerating sharply as it approached the star. It was a method of discovery that almost seemed to work against intuition. The planet did not appear in the data as a point of light. It appeared as the hidden cause behind the movement of something else. Humanity saw the star wobble slightly, and from that motion inferred the presence of a giant world beside it. This technique is known as the radial velocity method because it measures the part of the star's motion directed toward or away from Earth. It does not reveal the star's complete movement through space, only the component that lies along our line of sight. For this reason, the first estimate of a planet's mass is usually a minimum mass. If the orbit is tilted at an angle that makes the motion minimum harder to observe, the planet may actually be heavier than the value inferred from the signal. In the case of HD 80606b, later observations made the geometry of the system clearer. From Earth's point of view, the planet passes both in front of and behind the star, allowing scientists to combine several methods and estimate its mass and size more precisely. But at the time of its initial discovery, the star's changing radial velocity was the most important clue. It revealed the presence of a large object, several times more massive than Jupiter, moving along one of the strangest orbits ever recorded around a sun-like star. What is especially remarkable is that no single measurement could tell the entire story. One observation revealed only how quickly the star was moving toward or away from Earth at that particular moment. Only when many data points were placed together across weeks and months did the curve begin to emerge. The slowly changing sections corresponded to the long interval when the planet remained far away. The rapid shift in velocity reflected its plunge toward the star. The entire orbit was reconstructed from tiny movements hidden within the light. The process can be imagined as standing behind a wall and watching the shadow of a swinging pendulum. We cannot see the object itself, but from the rhythm of its shadow, the way it speeds up and slows down, and the moments when it changes direction, we can infer the shape of the motion behind the wall. For an exoplanet, the wall is a distance of hundreds of light years, and the shadow is replaced by spectral lines shifting back and forth across an instrument. Patience was just as important as precision. An orbit lasting 111 days could not be understood from only a few nights of observation. Astronomers had to return to the star repeatedly, measure the same spectral lines, examine possible errors, and wait for the signal to repeat. When the cycle appeared again with the same shape, the likelihood that it was merely noise or random activity within the star became much smaller. The invisible planet gradually became the most convincing explanation. From a very slight wobble, humanity learned that the star was not still. From the star's motion, scientists inferred that a massive object was pulling on it, and from the uneven rhythm of that pull, they recognized that the object was traveling along an elongated path, where most of the year passed slowly before its motion surged near the star. Here, science did not need a spectacular image to reveal an entire world. It needed only light stable enough to measure, instruments sensitive enough to detect the change, and people willing to watch a seemingly insignificant variation for a very long time. The more distant the planet, the fainter the signal becomes, but gravity still leaves a trace. No massive object can orbit a star without exerting some influence in return. Even so, the radial velocity method revealed only that the planet existed and how it moved. It did not directly show how large the world was, nor was it enough to isolate the heat radiating from its atmosphere. To measure the planet's size and follow its own light, astronomers had to wait for a more favorable geometric alignment. Fortunately, from Earth's perspective, the orbit of HD 80606b is tilted in a way that allows the planet to pass in front of the star at certain times and disappear behind it at others. During those brief events, the total light from the system changes by a tiny amount. And just as a subtle wobble first revealed the presence of a giant world, those later dips in brightness opened a deeper way of observing it, measuring the planet's size as it crossed in front of the star and separating its light when it vanished behind it. The wobble of the star revealed that HD 80606b existed, but the planet remained an invisible presence, inferred only from the gravitational pull it exerted on its parent star. To go one step further, astronomers needed a more favorable alignment, one in which the light from the entire system changed clearly enough to separate the planet's signature. Fortunately, from Earth's point of view, the orbit of this world is aligned almost exactly as needed. During each orbit, there comes a time when the planet passes in front of the star. It does not block the star completely, because it is far smaller, but it still covers enough of the stellar disk to prevent a small portion of the light from reaching us. The total brightness of the system dips slightly, remains lower for a while, and then returns to its previous level as the planet moves away from the face of the star. This event is known as a transit. No one could detect the change with the naked eye. The star does not suddenly become noticeably dimmer, nor does the planet appear as an easily visible black dot. The signal is only a slight decrease in the amount of light collected by the telescope. Yet, when measurements are precise enough and taken continuously, the light curve begins to assume a familiar shape. The brightness remains steady, gradually falls as the planet moves in front of the star, stays at a lower level, while part of the stellar disk is blocked, and then rises again when the passage ends. The depth of the missing light is related to the size of the planet. A large world blocks more light than a small one. So while the radial velocity method provides an estimate of mass, a transit offers a clue to radius. When those two pieces of information are placed together, scientists can approximate the planet's density and begin to understand what kind of world it is. A dense rocky planet, a lighter gas giant, or an enormous sphere, with a structure somewhere between those possibilities. For HD 80606b, this combination revealed an extremely massive gas giant whose size had not expanded in proportion to its mass. It contains far more material than Jupiter, but its powerful gravity also compresses the atmospheric layers more tightly. What had once appeared only as a wobble in a spectrum now began to take on a clearer form. A huge, heavy world traveling along an elongated orbit and occasionally crossing the face of its star. But the transit revealed only how much light from the parent star the planet blocked. To learn how much heat the planet itself was emitting, astronomers had to wait for an almost opposite moment, the time when it passed behind the star and temporarily disappeared from view. For most of the orbit, telescopes receive the combined light of the entire system. The star contributes nearly all of the visible light, while the planet adds only a tiny amount, mostly in the infrared, where its warm atmosphere radiates energy. The two sources blend so completely that they are almost impossible to separate in a single image. But when the planet moves fully behind its parent star, the light coming from the planet is hidden for a short time. The telescope then receives only the light of the star. This event is known as a secondary eclipse. The measurement is elegantly simple. Before the planet disappears, the telescope records the light from the star together with the light and heat from the planet. While the planet is hidden, only the star remains. Subtracting one level from the other reveals the tiny contribution from the planet itself. We can imagine a room where a large lamp and a candle are burning together. When both are lit, the candlelight is almost overwhelmed. But if the candle is covered for a few seconds, while the lamp remains unchanged, the slight decrease in brightness between those moments represents the light the candle had been contributing. In this distant star system, the difference is far smaller, but the principle is much the same. What makes the secondary eclipse of HD 80606b especially valuable is that it occurs near the time when the planet passes through periastron, and its temperature is changing rapidly. This allows telescopes to do more than measure how hot the planet is in a stable state. They can follow it before, during, and after the close approach. The infrared light curve rises as the atmospheric layers are heated, changes as the hot region shifts, and then suddenly loses part of its signal when the planet disappears behind the star. That moment of disappearance is like briefly turning off a small light inside a room already filled with brightness. The planet's temporary absence allows us to measure its presence more clearly. While it remains visible, its light is blended with the light of the parent star. When it passes behind the star, its contribution is removed from the total signal, leaving behind a measurable deficit. From the depth of the secondary eclipse at different wavelengths, scientists can infer how much heat the atmosphere is emitting. If the planet appears brighter in the infrared, the observed layers may be hotter, or they may allow radiation from deeper regions to escape more easily. If the brightness changes over time, the signal may reflect the way the atmosphere heats up, retains energy, and redistributes it after the intense warming near the star. Each wavelength probes a slightly different part of the atmosphere. Some wavelengths are more sensitive to the upper layers, where starlight is absorbed first. Others may carry information from deeper regions, where heat is retained for longer. By placing these light curves beside one another, astronomers can learn not only how the overall temperature changes, but also begin to see the depth of the process, which layers respond quickly, which respond more slowly, and which continue holding heat after the planet has left the closest region. Interpreting these signals, however, is not as simple as seeing a dip in brightness and immediately drawing a conclusion. The star has subtle variations of its own. Instruments can be affected by temperature, position, and many other delicate sources of error. Each change must be examined carefully, compared across multiple observations, and tested against different models to distinguish the planet's true signal from noise. That is why the hours surrounding a secondary eclipse are so valuable. The telescope must observe the system continuously before the planet disappears, while it is hidden, and after it re-emerges. Only with enough data from both sides of the event can researchers determine how the background brightness is changing and which portion truly belongs to the planet. Here, the geometry of the orbit becomes a rare gift. Not every exoplanet passes directly in front of and behind its star from Earth's point of view. Most orbits are tilted so that the planet always moves slightly above or below the stellar disk in our line of sight. For HD 80606b, the favorable inclination opens two observational windows. One when the planet passes in front, allowing its size to be measured, and another when it moves behind, allowing its own light and heat to be separated from the stars. Through these two disappearances, a world too distant and too faint to be seen directly gradually becomes more tangible. Its mass is revealed by the wobble of the star. Its size is measured during the transit. Then the heat of its atmosphere can be detected when the planet temporarily vanishes behind the star. Each method provides only one part of the picture, but together they build up the layers of a portrait. There is a quiet beauty in the way we learn these things. No probe needs to be sent to a star system hundreds of light years away. No individual cloud needs to be photographed. We only need to watch the light for long enough, notice when it fades slightly, and patiently determine what the missing portion belongs to. Before the transit, the planet was recognized through gravity. During the transit, it appeared through the light it blocked. When it passed behind the star, it was detected through the very light that could no longer reach us. A world that cannot be seen directly has revealed itself again and again through tiny absences. These methods opened the way for a new generation of telescopes. Before the James Webb Space Telescope followed the temperature surge in greater detail, another infrared observatory had already detected the first heat wave on this planet. Those early data were limited, but they were enough to show that HD 80606b possessed more than an unusual orbit. Its atmosphere truly did heat up rapidly as the planet approached its star. From that moment on, the planet was no longer merely a data point in a catalog. It became a world whose weather could be followed from afar, where the light rose, disappeared, and returned, gradually telling humanity what was unfolding inside an atmosphere no one could ever touch directly. Before the James Webb Space Telescope could look more deeply into the atmosphere of HD 80606b, another telescope spent many hours watching that distant star system, waiting for a change that no one had ever observed so clearly before. It was not searching for the shapes of clouds, nor was it trying to photograph a globe beside the star. Its task was simpler to describe, but far more difficult in practice. To listen for the exceedingly faint heat the planet released into space, then follow how that signal changed as the entire world rushed through the point of closest approach. That telescope was Spitzer, a space observatory designed to view the universe in infrared light. Infrared is invisible to human eyes, but every object with a temperature radiates some of its energy in this part of the spectrum. A warm cup on a table, the ground after a sunny day, and a gas giant hundreds of light years away all leave thermal signatures of their own, differing only in intensity and wavelength. Spitzer did not see heat as a vivid red glow in a picture. It measured extremely faint infrared photons and turned them into a light curve that could be followed over time. This made it the right instrument for HD 80606b. In visible light, the star almost completely overwhelms the planet. But in the infrared, the heat radiated by the atmosphere becomes slightly easier to detect. Here, easier still means separating a tiny variation from the light of a star many times brighter, while keeping the instrument stable for hours to ensure that the rise in brightness truly comes from the planet rather than from noise or changes within the telescope itself. In November 2007, Spitzer began observing the system about 20 hours before the planet reached the closest point in its orbit. The telescope continued watching throughout the encounter and for roughly 10 hours afterward. Altogether, it collected nearly 30 hours of continuous data, long enough to watch a world move from a less intensely heated state into the region of strongest radiation and then begin its retreat. 30 hours is not a long time in astronomy. Many stars change over millions of years, galaxies evolve over billions, and the complete orbits of some distant objects may require decades of observation. But for this planet, 30 hours contained nearly the entire defining event of its 111-day year. The long week spent in the distant region became a quiet background, while the brief close approach was where the infrared light began to rise like a wave. At first, the signal remained almost unchanged. The planet was still moving inward, but the atmosphere had not yet responded strongly enough to produce a major difference. Then the light curve began to climb. There was no sudden switch, no single moment when the entire world entered a new state at once. The brightness rose at an accelerating pace, reflecting upper atmospheric layers, absorbing more energy and radiating heat more strongly into space. Over about 6 hours, the thermal brightness measured by Spitzer in one infrared band indicated that the apparent temperature had risen from around 800 Kelvin to nearly 1,500 Kelvin. This was not a single temperature representing the entire planet, but a value inferred from the layer of gas, radiating strongly at the wavelength Spitzer observed. Even so, the change was large enough to confirm what had previously existed mainly in models. The atmosphere truly did heat at an extraordinary rate as the planet swept past its star. We can imagine that light curve as a thermometer placed unimaginably far away, never touching the planet, and never measuring each atmospheric region directly. It recorded only the combined thermal energy traveling toward Earth. As the curve rose, astronomers knew that the observable atmosphere was radiating more energy. As its shape changed, they began to recognize the rate of heating, the moment when the hot region rotated into view, and the atmosphere's ability to retain or release heat. The moment when the planet disappeared behind the star made the measurement even more valuable. For a short time, the thermal contribution from HD 80606b vanished from the signal, leaving almost nothing but the light of the star. That absence allowed researchers to determine how much the planet had contributed before and after the eclipse, rather than merely knowing that the overall brightness had changed without knowing its starting level. By disappearing for a few hours, the world unintentionally provided the clearest reference point for measuring its own temperature. What Spitzer saw was not an image of a storm or a complete map of the hot region. It was a simple infrared light curve, but within that curve lay the motion of an entire atmosphere. The rapid rise in heat suggested that energy from the star was being absorbed mainly in relatively high layers, where the amount of gas was small enough to warm within a few hours. If the energy had needed to penetrate much deeper into denser layers before being radiated back outward, the response would probably have been far slower. The way the planet cooled was just as important as the way it heated. After it passed periastron, the incoming radiation began to weaken, and Spitzer followed whether the thermal brightness remained elevated or declined quickly. The results suggested that the observed atmospheric layers could release heat relatively rapidly. This did not mean that the planet's entire interior cooled within a few hours. The deeper regions still possessed enormous thermal inertia, but the gas emitting within Spitzer's observed band responded to the close approach far more quickly than is typical of more stable atmospheric environments. For the first time, astronomers were not merely measuring an exoplanet in a hotter or cooler state. They were watching that state change in real time. A world beyond the solar system no longer appeared as a fixed number in a table of data. It had an afternoon of rising heat, a hot region that developed and spread, and an interval of gradual cooling after the strongest light had receded. This marked an important shift in the way humanity studied distant planets. Earlier, atmospheric measurements had often resembled snapshots taken at a single moment, an average temperature, a brightness at one wavelength, or the signature of a molecule. With HD 80606b, Spitzer turned the observation into a very simple movie, lacking clear images but carrying a rhythm through time. Each data point became a frame, and together they revealed an atmosphere responding to a changing source of heat. Computer models later used this curve to recreate how energy might spread across the planet. If the modeled atmosphere retained heat for too long, its light curve would decline more slowly than the observations. If winds carried the hot region away too quickly, the brightest moment would occur at the wrong time. By adjusting the atmospheric response, gas motion, and planetary rotation, researchers gradually found scenarios that better matched the signal Spitzer had recorded. Yet Spitzer still viewed this world through a relatively narrow window. It could measure infrared brightness very precisely at certain wavelengths, but it could not separate the atmosphere into detailed chemical layers as later generations of telescopes would. Its light curve revealed how the planet heated and cooled, but it could not fully answer deeper questions: which molecules were absorbing the energy, how the clouds were changing, or how differently each atmospheric altitude responded. Even the inferred temperature had to be understood within the limits of the observed wavelength. A layer glowing strongly in the infrared did not represent every region of the planet. The upper atmosphere might heat rapidly, while deeper layers changed more slowly. A hot region rotating into view could raise the total brightness even if the entire hemisphere had not reached the same temperature. Spitzer had opened the door, but many layers beyond it remained indistinct. Still, the value of that observation did not lie in answering every question. It lay in proving that those questions could be addressed with data. The climate of an exoplanet was no longer entirely beyond our reach. Humanity could follow a surge of heating, measure the atmosphere's delay, and test whether models of wind and energy retention came close to reality. For many years afterward, Spitzer's light curve became the foundation for deeper studies of HD 80606b. Scientists returned to the data, built better three-dimensional models, and added the possible effects of every new model faced the same test. Could it reproduce the wave of heat that Spitzer had observed? There is a quiet beauty in this story. The telescope never saw the planet in a clearly defined shape, but it detected the warmth of the world rising. From a subtle change in infrared light, humanity learned that the upper atmospheric layers were being heated, that the hot region was moving, and that an entire atmosphere could transform within the span of a single long day on Earth. Spitzer gave us the first outline of the encounter between the planet and its star. But that outline remained faint, like a picture painted with only a few shades of heat. To look deeper into the atmospheric composition, follow several layers at once, and separate more clearly what happened before, during, and after the close approach. Humanity needed a telescope capable of collecting infrared light with greater sensitivity and detail. Many years later, the James Webb Space Telescope turned toward the same star system and continued where Spitzer had left off. This time, the goal was not only to watch the heat wave rise, but to open it into a broader spectrum, where each wavelength could tell a different part of the story. Spitzer had shown that the atmosphere was changing. Webb would begin asking more deeply where that change occurred, how powerful it became, and what traces it left within the planet's own material. Spitzer had watched the atmosphere heat like a rising wave sweeping across the planet, but the light curve it left behind was only the first outline. Humanity knew that the heat was increasing rapidly, and that the world was changing within only a few hours, but could not clearly separate what was happening within each atmospheric layer. Heat from the upper atmosphere, warmth retained deeper below, the influence of clouds, and the signatures of molecules were still blended into the same faint signal. Many years later, the James Webb Space Telescope returned with the goal not only of seeing that wave, but of opening it up to discover what lay within. The observation was arranged around the briefest and most important part of the planet's 111-day orbit. Webb turned toward the star system while the planet was still moving inward, continued watching through the hours of closest approach, and remained as it swept around to the other side. That interval was like a window opening only for a moment. If it were missed, the telescope would have to wait through another orbit, and even when the planet returned, Webb's position and the limits of observing from space might not allow it to point in the right direction. So when the final window opened, Webb did not simply capture a few isolated moments. It quietly followed the light of the entire system through a long, continuous sequence, allowing each subtle change to connect with the next. At the beginning of the observation, the star was growing larger in the planet's sky. Near the middle, the giant gaseous world passed through the region of strongest radiation. Toward the end, the distance began increasing again, while the atmosphere continued carrying the heat it had just received. The instrument used was MIRI, Webb's mid-infrared eye. In this region of light, invisible to human vision, a heated atmosphere gives off a glow of its own. Webb collected that light, but instead of measuring only its overall brightness, the telescope separated it into many wavelength bands. The signal no longer resembled a single sustained note. It became a series of different tones, each one potentially emerging from a different altitude or being shaped by a different kind of molecule. This is what allowed Webb to go beyond Spitzer. A thin layer high in the atmosphere may heat quickly as the starlight intensifies, while deeper regions respond more slowly and retain warmth for longer. When only the total brightness is measured, these two responses can easily blend together. But when the light is divided into separate wavelength bands, researchers can follow which part brightens first, which reaches its peak later, and which continues holding heat after the planet has already begun moving away. We might imagine the atmosphere as a multi-story house, when the heating system is suddenly turned much higher. The floor nearest the heat source warms first, hallways carry warmth into other rooms, and spaces deeper inside respond more slowly. A single thermometer outside the front door would reveal only that the whole house was warming. But with sensors placed in different locations, the delay between floors would begin to emerge. Webb cannot place sensors directly inside the planet, but infrared wavelengths perform something remarkably similar. During the observation, the planet also passed behind its star. This moment has already been described as the brief disappearance of the planet's tiny contribution from the system's total light. For Webb, that disappearance became an essential reference point. Before the eclipse, the telescope received the light of the star together with the far weaker thermal glow of the planet. While the world was hidden behind its parent star, its contribution temporarily stopped reaching the telescope. The difference allowed scientists to determine which portion of the light truly belonged to the heated atmosphere. When the first data were examined, one striking change quickly became visible. The temperature of the atmospheric region Webb was tracking rose by about 1,100 degrees Fahrenheit, or more than 600 degrees Celsius, as the planet swept through the region near its star. This increase was even greater than some earlier interpretations of the Spitzer data had suggested. But this number does not mean that the entire planet became more than 600 degrees hotter all at once. There is no single thermometer that represents every atmospheric layer, every illuminated and dark region, and every depth. Webb measures radiation escaping from the layers visible within the infrared range of the instrument. The side facing the star, the darker side, the upper atmosphere, and deeper regions may all remain in very different states. What the telescope detected was a dramatic change in the portion of the atmosphere, contributing most clearly to the signal. What makes the data especially rich is the way the temperature changes across different wavelengths. Some bands respond quickly, as though they are emerging from atmospheric layers that receive the heating almost immediately. Others change more slowly, suggesting that their radiation comes from regions where warmth is retained for longer. When these signals are placed side by side over time, researchers begin to see not merely a planet growing hotter, but an atmosphere with depth, where each layer enters the close encounter according to its own rhythm. The light may also reveal chemical composition. Molecules such as methane and carbon dioxide do not absorb every wavelength equally. They leave subtle signatures in the spectrum, like uniquely shaped silences within a piece of music. Webb is sensitive enough to begin distinguishing these features more clearly than earlier telescopes, but that does not mean a complete inventory of the atmosphere appeared immediately. The data are too rich to be explained with a single glance. Temperature changes continuously throughout the observation. Clouds may conceal or reveal different atmospheric layers, and winds carry matter through hotter and less intensely heated regions. A weakening feature might mean that a molecule has become less abundant, but it could also mean that the cloud layer above has thickened. A brightening region of the spectrum may reflect rising temperature, or it may indicate that the heat has thinned the clouds and allowed radiation from deeper below to escape more easily. For this reason, scientists are still separating the dataset layer by layer. They compare the light at different moments, test a range of atmospheric models, and examine which explanation can account for temperature, clouds, and chemistry at the same time. The early results clearly reveal the sudden heating, but the finer details of individual molecules and the way they change around the close approach remain an unfinished story. This is not a disappointing limitation. On the contrary, it shows that Webb has brought humanity to a new level of observation, where the question is no longer whether we can see the planet changing. That change is now unmistakable. The questions have become where it begins, how it spreads, how the clouds respond, and whether the atmospheric chemistry can keep pace with the rapid shift in temperature. HD 80606b is especially valuable because nature has compressed several climate states into a single observation. On a hot Jupiter that always remains close to its star, telescopes usually see an atmosphere after it has spent a very long time under intense heating. We see the result, but it is difficult to observe the process that created it. Here, the same world moves from a less intensely heated state into a violent temperature surge, then quickly retreats. Webb can follow the atmosphere before the disruption, while the change is unfolding, and as it begins finding its way back toward a calmer state. It is like watching a room from the moment the heater is first turned on, rather than entering only after the room has been warm for a long time. The data allow us to trace the entire process. What we learn, therefore, applies not only to one unusual planet. It also helps test the way models describe heat transport, winds, clouds, and chemistry on many other hot gas giants, including worlds with less extreme orbits. Spitzer began the story by seeing the thermal brightness rise. Webb continued it by separating that brightness into multiple layers of information. The two telescopes did not replace one another. They were more like two observers standing in different eras. One recognized from a distance that the atmosphere was changing. The one that followed could move deeper into the details and begin identifying the traces hidden within that transformation. Even so, Webb still does not see the planet as a sharply defined globe. There is no movie showing cloud bands dissolving under the starlight, and no complete map of hot regions drifting around the world. Everything is still interpreted from a tiny amount of light overwhelmed by the star. Yet, within that subtle change, humanity has detected a temperature surge of hundreds of degrees, differences between atmospheric layers, and chemical signatures still waiting to be decoded. The atmosphere has told Webb what is happening in the present. It has shown how rapidly the heat arrives, which regions of gas respond first, and how the close encounter continues to echo afterward. But the same observation also brings an older question into sharper view, one that lies beyond the clouds and winds. Why does a giant gas planet follow a path that carries it so extremely close to its star? An orbit this elongated is difficult to regard as a random detail. It may be the surviving trace of a gravitational process that began long ago, when another object in the system quietly pulled, tilted, and reshaped the planet's path over millions or billions of years. Webb has opened a deeper view into the atmosphere. To understand why that atmosphere must endure the same intense heating every 111 days, we must step farther back and look into the history of the entire star system. The James Webb Space Telescope is helping humanity read the changes unfolding in the atmosphere of HD 80606b today. But the planet's orbit tells a story from a far more distant past. The path that returns this giant gaseous world to the furnace every 111 days may not be the path it followed in the beginning. A planet several times more massive than Jupiter would have had difficulty forming so close to its star, where temperatures are high and the materials needed to build a large gas giant are less abundant. More likely, it was born farther away, in a broad and relatively stable orbit, before gradually being guided into the extreme path we see today. An important clue lies beyond the planetary system, close to the star. HD 80606 is not entirely alone. Far away lies a companion star called HD 80607. The distance between the two stars is so great that, over a human lifetime, they would appear almost motionless beside one another. Yet gravity still binds them, and together they move within a very wide binary star system. That distant star does not directly heat the planet. Its light is far too weak at the location of HD 80606b to cause the temperature surge of hundreds of degrees observed by Webb, nor does it wrench the planet from its path in a single violent event. Its influence is far subtler, a small gravitational pull, repeated through countless orbits and accumulated over spans of time longer than the entire history of humanity. In the universe, a weak influence is not necessarily a meaningless one. If the direction and rhythm of the pull are aligned in the right way, it can gradually tilt an orbit and then change how elongated that orbit becomes. The planet continues circling its primary star, but its path no longer preserves the same shape. Over time, orbital inclination and eccentricity can trade places with one another. As one decreases, the other increases, causing the orbit to cycle between relatively modest elongation and an extremely stretched form. This process is known as the Kozai-Lidov mechanism. The name may be difficult to remember, but the underlying idea is not so unfamiliar. Imagine a ring spinning steadily, while a small external force repeatedly pulls it off balance in the same rhythm. No single tug is strong enough to break the ring apart, but after many cycles, the plane and shape of its motion may change noticeably. For a planet, this transformation does not unfold over days or years, but may require millions of years. If this mechanism once operated strongly in the HD 80606 system, the planet's original orbit may have gradually become more elongated. Its farthest point remained in the outer region, while its closest point moved deeper toward the star. During each larger cycle, the planet experienced periods when it passed closer to its parent star than before, even though it still spent most of its time farther away. A world that once lived beneath a relatively stable source of light began enduring increasingly intense and repeated close approaches. But stretching the orbit is only half the story. Each time the planet passes very close to the star, gravity does not pull equally on both sides of it. The side facing the star is pulled more strongly than the far side, causing the entire gaseous sphere to deform slightly. Layers of matter within the planet are compressed, stretched, and displaced as it sweeps through periastron at tremendous speed. This is a tidal effect, based on the same fundamental principle that creates ocean tides on Earth, but operating far more intensely. HD 80606b has no surface ocean, yet its entire mass of gas can still be stretched slightly. The deformation does not occur perfectly smoothly. Layers of matter rub against one another and move out of alignment, converting part of the planet's orbital energy into internal heat. Each close approach removes only a tiny amount of energy. Across a few 111-day orbits, the path appears almost unchanged. But after an enormous number of passages, those small losses can accumulate. The orbit gradually contracts, while the point nearest the star continues to experience strong tidal effects. In this way, the planet may migrate inward from the distant region where it formed without requiring a single collision or one sudden catastrophic event. The distant companion star and the tides near the primary star may have worked together in this way. The second star slowly tilted and stretched the orbit through long gravitational cycles. Whenever the eccentricity became large enough, the planet moved extremely close to its parent star, where tides removed some energy from its motion. Gradually, the orbit shrank, leaving HD 80606b on the 111-day path it follows today, still extremely elongated, but much closer to the star than the region where a massive gas planet was likely born. Another clue supporting this history lies in the direction of the planet's motion. In a system that forms relatively calmly from the same disk of gas and dust, planetary orbits are usually aligned with the equator of the star. The entire system is shaped within roughly the same plane. But measurements show that the orbit of HD 80606b is significantly tilted relative to the rotation of its parent star as seen from Earth. This misalignment is not absolute proof that the Kozai-Lidov mechanism created the planet's present orbit. It is, however, consistent with a past disturbed by an external gravitational influence. A planet migrating gently within its original disk generally tends to preserve better alignment, while a planet pulled and tilted over long periods is more likely to leave behind a more disordered structure. Even so, we have never directly observed this process from beginning to end. A single large cycle may last far too long for humanity to witness in full. What scientists have instead is the system as it exists today, the shape and tilt of the orbit, the presence of the companion star, and models showing how these elements may be connected. This history should therefore be understood as a well-supported explanation, not as a complete movie of the past. The young star system may have been more complex than what remains today. The original disk of gas, other gravitational interactions, or poorly understood stages of evolution may also have helped shape the planet. But whatever details are still missing, its extreme orbit almost certainly points to a history that was never entirely calm. There is something beautiful in the idea that a star so distant from the planet may still be connected to the weather in its atmosphere. The companion star does not send the burst of heat that raises temperatures by hundreds of degrees, but its gravity may have helped create the path that carries the planet into the region of intense radiation. That path produces the sudden heating, and the heating creates the pressure differences, winds, clouds, and chemical changes that telescopes are now trying to understand. A weak pull acting over millions of years can ultimately leave its mark on events lasting only a few hours. The orbit therefore becomes a bridge between the history of the entire star system and the weather unfolding in the present. Each time HD 80606b returns to the furnace, it repeats the consequence of an ancient gravitational process. The atmospheric layers heating today may be responding to a path shaped long before Earth existed. But tides do not belong only to the past. If every close approach converts some orbital energy into heat, the planet's evolution may still be continuing, though too slowly to detect over only a few years of observation. Across very long spans of time, the orbit may become more circular. The distance between the planet and its star may change, and the present 111-day rhythm of heating may not last forever. This brings the story back to one final question. HD 80606b has survived countless plunges into intense radiation without falling into its star, but how long can that balance endure? To understand the future of this world, we must first see clearly why gravity can draw it so deeply inward during every close approach, yet still fail to hold it beside the furnace. When HD 80606b sweeps past the point closest to its star, everything happens too quickly for the atmosphere to recover its balance. The light intensifies, temperatures surge, winds are driven into motion, and the upper layers of gas glow more brightly in the infrared. Yet even as the world seems to be plunging deepest into the furnace, its orbit has already begun carrying it in the opposite direction. The star does not release the planet. Gravity continues pulling it inward just as before. What changes is its velocity. As HD 80606b falls toward the star, it accelerates continuously. At periastron, it is moving faster than at any other point in its orbit. That speed does not carry the planet directly away. Instead, it sends the world sweeping sideways through the closest region, while gravity bends its path into a narrow arc. The planet continues falling toward the star, but it falls past it quickly enough that it never arrives. This is the quiet nature of an orbit. There are no invisible tracks holding the planet in space, and no force pushes it back outward after each close approach. There is only gravity existing together with motion, turning a fall into a long curve around the star. HD 80606b does not escape the furnace at the final moment. It was never truly falling into it. Periastron is simply the place where the orbit brings the planet closest before its velocity carries it around to the other side. The atmosphere also survives in a way less dramatic than the image of passing through fire might suggest. No actual flames surround the planet. What it receives is intense radiation, transferring energy into the atmospheric layers and heating them rapidly. The upper atmosphere responds first because it contains less material and can change within a few hours. The deeper layers are far denser, allowing them to preserve their earlier state for longer. HD 80606b is also an extremely massive planet. Its powerful gravity helps it hold on to most of its atmosphere even when the outer layers expand and are stirred by the heat. The close approach also lasts only a short time. The planet does not remain beside the star at its minimum distance throughout the year. It passes through that region and quickly begins moving away. The heating is therefore strong enough to transform the weather, but it does not last long enough to force the entire world into a completely new state. The upper atmosphere may warm by hundreds of degrees, while most of the mass below responds more slowly. Some of the energy is carried away by winds, some moves deeper into the planet, and some is radiated back into space as the world continues outward. Even so, every passage leaves an after effect. The hot region does not disappear the moment the distance begins to increase. Winds continue redistributing heat, clouds need time to form again, and chemical reactions may respond even more slowly than the changing light. The planet has left periastron, but its atmosphere is still living within the hours that have just passed. Farther below, tides are also quietly changing the orbit. During each close approach, the planet is deformed slightly by gravity, and some of its orbital energy is converted into internal heat. The change after one revolution is far too small to notice, but across immense spans of time, it may make the orbit less elongated and gradually more circular. This means the violent cycle we see today may not last forever. In the distant future, the planet may no longer alternate between a relatively quiet region and a brief, intense, close approach. It may settle into a more even orbit, where the incoming heat no longer rises and falls so abruptly. For now, however, the 111 day path continues. That repeating rhythm has made HD 80606b one of the most remarkable natural laboratories for studying planetary atmospheres. Most hot gas giants orbit close to their stars along nearly circular paths. They receive intense heating continuously, so astronomers usually observe atmospheres that have lived under hot conditions for a very long time. HD 80606b is different. The same planet can be observed while it is still far away, as the heating begins to rise, during the hours of greatest intensity, and as it starts cooling again. Instead of seeing only the final result, humanity can follow the entire process. Spitzer was the first telescope to watch the heat wave rise. The James Webb Space Telescope returned with more detailed infrared observations, opening the possibility of probing several atmospheric layers, distinguishing their different heating rhythms, and searching for chemical signatures still hidden within the spectrum. From hundreds of light years away, no one can directly see the planet's winds or cloud layers. Yet a slight wobble in the star's light revealed its mass. A transit revealed its size. The moment it disappeared behind the star allowed scientists to separate the heat emitted by the planet itself. And tiny changes over time revealed an atmosphere in motion, heating rapidly and then slowly becoming gentler again. Perhaps this is the most beautiful lesson the world leaves behind. Science does not need to see every detail in order to understand something profound. Sometimes, a slight shift in a line of light, a small dip in brightness, or a rising infrared signal is enough to reveal an entire planet with weather, history, and a rhythm of its own. HD 80606b also shows that the climate of a world does not begin only within its atmosphere. It begins with the shape of its orbit, the gravity of its star, the distant influence of a stellar companion, and changes unfolding over millions of years. A faint gravitational pull in the past may determine how much light enters the atmosphere today. That light then becomes heat, wind, clouds, and finally the traces that telescopes are able to read. The planet has now passed through the most violent part of its orbit. The star is growing smaller in its sky, the upper atmosphere continues releasing heat, and the winds slowly carry the remaining energy away from the region that was heated most intensely. Wherever temperatures remain gentle for long enough, cloud particles may begin appearing again, thin and scattered at first, then gradually concealing the deeper layers. There is no clear boundary between the end of the close approach and the return of calm. Every change unfolds gradually. Heat slowly leaves the atmosphere, winds slowly weaken, and chemistry slowly finds its way toward a more stable state. For most of the remaining journey, the giant gaseous world will continue drifting through the distant region, carrying the fading memory of its latest passage through the fire. Then another orbit will begin. The distance will shrink again, the planet will accelerate, and the star will once more grow larger ahead. But that is a story for another time. For now, the planet is still moving outward, and its long interval of rest has only just begun. Thank you for joining Sleep Gravity on this journey with a world that returns close to its star every 111 days. Now, as HD 80606b continues drifting into the darker reaches of its orbit, while the heat softens within its deep atmosphere and unfamiliar clouds slowly begin to form again, you can allow the planet to recede gently in your mind. Its orbit continues hundreds of light years away, while here, every motion can quietly begin to slow, allowing the rest of the night to open more softly, more deeply, and more peacefully.